What does Dinar reveal about Sumer's people? In a climate-controlled laboratory beneath the University of Pennsylvania Museum, a researcher in sterile gloves holds the answer: a fragment of bone, no larger than a thumbnail, excavated from the Royal Cemetery of Ur nearly a century ago. The fragment is ivory-coloured, surprisingly light, its surface marked by the fine texture of ancient cortical tissue. It spent 4,500 years in the Mesopotamian earth before Leonard Woolley's expedition unearthed it in 1928, and another 90 years in museum storage before anyone thought to ask what secrets might be locked inside its cellular structure. The extraction protocol is delicate. Ancient dinar degrades, breaks into smaller and smaller fragments with each passing century. Contamination from modern handlers, from soil bacteria, from the very air itself can overwhelm the faint genetic signal that remains. The researcher works in a room maintained under positive pressure, wearing full protective equipment, using tools sterilised by ultraviolet light. A small sample, mere milligrams, is removed from the interior of the bone where contamination is least likely. Chemical solutions dissolve the mineral matrix, releasing whatever genetic material has survived the millennia. The liquid is clear, unremarkable to the eye, but it contains something extraordinary, molecules that carry information about who these people were, where they came from, and whether the claims recorded in their oldest texts might be something other than mythology. The Sumerians themselves left explicit records about their ancestry. On thousands of cuneiform tablets, in temple hymns and royal inscriptions, in creation narratives and genealogical lists, they described their bloodlines as divine. Not metaphorically divine, not symbolically connected to the gods, but descended through specific named lineages from beings they called the Anunnaki. Kings traced their authority to these bloodlines. Priestesses embodied them in ritual. The entire structure of Sumerian civilization rested on the premise that some humans carried something in their blood that others did not, something inherited from a time before the cities, before the flood, before memory itself. Modern genetic science has now developed the tools to test such claims, or rather, to test whether anything in the genetic record corresponds to what the texts describe. The bone fragment from Ur is one of dozens collected from Mesopotamian sites, part of a broader effort to map the ancestry of the world's first complex civilization. The results, published in peer-reviewed journals over the past several years, reveal patterns that the researchers themselves describe with caution and careful qualification. The ancient Mesopotamian populations show evidence of admixture, the technical term for genetic mixing between distinct ancestral groups. They carry markers indicating origins from multiple regions: Anatolia, the Caucasus, the Levantine coast. The proportions of these ancestries vary between individuals, between sites, between time periods, and in some cases the genetic data shows discontinuities, population replacements, the arrival of new peoples whose dinar differs measurably from those who came before. The Sumerian texts describe exactly these events. They speak of mixing, of divine essence combined with earthly clay, of bloodlines that bridge the terrestrial and the celestial. They record a great flood, after which the kingship was lowered again from heaven, implying new populations, new rulers, new blood. They preserve the names of those who came before, the Anunnaki themselves, and describe with procedural precision how humanity was created through a process that involved substances from two sources, one indigenous to Earth, one decidedly not. What does Dinar reveal about Sumer's people? Perhaps that their oldest stories, dismissed for centuries as primitive mythology, preserve memories of actual events, migrations, admixtures, the encounter between populations so different that their genetic signatures remain distinct in the molecular record 5,000 years later. Or perhaps that human populations everywhere carry complex ancestries, and the Sumerians simply documented theirs with unusual specificity. Or perhaps something stranger, that the correspondence between genetic evidence and ancient narrative is too precise to dismiss, too problematic to accept, and most intriguing when we resist the urge to explain it away. If you're listening to this in the quiet hours, wherever you are in the world, drop a comment with your location and the time. There's something appropriate about exploring these questions in darkness, when the boundary between sleep and waking mirrors the boundary between what we can prove and what we wonder about. The Sumerians themselves wrote some of these texts for nocturnal rituals, hymns performed in temple courtyards under stars that still shine on the ruins of Ur. The bone fragment has now been returned to its storage container, its genetic material sequenced and catalogued. But the questions it raises are just beginning. To understand what Dinar reveals about Sumer's people, we need to start with who they were, where they appeared, and why their origins remain, even after a century of archaeology, one of the most enduring mysteries of human prehistory. Who were the Sumerians? The Sumerians emerge in the archaeological record of southern Mesopotamia around 5400 BC at sites like Eridu and Uruk, along the lower reaches of the Tigris and Euphrates rivers in what is now southern Iraq. They emerge rather than arrive because no clear migration route explains their presence. The pottery traditions, architectural styles, and tool technologies that characterize early Sumerian sites show continuity with the preceding Ubaid period, suggesting cultural evolution from earlier inhabitants. But the Sumerian language itself tells a different story. It belongs to no known language family. It shares no demonstrable relationship with the Semitic languages spoken by their neighbours, no connection to the Indo-European languages spreading across Eurasia, no links to any other language group identified by linguistics. It stands isolated, a linguistic singularity in the ancient Near East. This linguistic isolation has puzzled scholars since cuneiform was first deciphered in the 19th century. Languages don't typically evolve in complete isolation. They borrow words from neighbours, share grammatical structures with related tongues, carry markers of their origins and connections. But Sumerian, as far as analysis can determine, relates to nothing. It's been compared to Uralic languages, to Dravidian languages of India, to isolated languages of the Caucasus, but no comparison yields convincing evidence of relationship. It exists as if it arrived fully formed, or as if its speakers came from somewhere whose other languages left no trace in the historical record. The Sumerians themselves, in their later texts, claimed they came from a place called Dilmun, often identified with the island of Bahrain in the Persian Gulf, though some texts suggest Dilmun was more concept than place, a primordial land, the site of creation itself, somewhere to the east, across water. Other texts make no mention of migration at all, presenting the Sumerians as indigenous, created in place by the gods, specifically by Enki, the god of wisdom and underground waters, who made his home in Eridu, the oldest city, the first settlement where kingship descended from heaven. The archaeological picture shows something more nuanced than simple migration. The site of Eridu, excavated extensively in the 1940s and 1950s, reveals a sequence of temple constructions spanning nearly 2,000 years, each built directly atop the ruins of the previous structure. The earliest temples, dated to around 5400 BCE, are small, modest platforms with simple shrines. But they're positioned with astronomical precision, oriented to celestial events, built according to proportional systems that suggest sophisticated mathematical knowledge. The progression from these early structures to the massive ziggurats of the later Sumerian period shows continuity of sacred space, continuous occupation, a people who stayed in place for millennia and developed their civilization vertically, building upward in the same locations rather than spreading outward and abandoning old sites. Yet during this same period, genetic evidence from the broader region shows multiple population movements. The Neolithic period in Mesopotamia, from roughly 10,000 to 5,000 BC, witnessed the arrival of farming populations from several directions. Genetic studies of ancient skeletal remains reveal a mixture between local hunter-gatherer populations and incoming agriculturalists. These farmers carried genetic markers linking them to the Caucasus, to Anatolia, to the Zagros Mountains of western Iran. The mixing of these populations created the genetic landscape of ancient Mesopotamia, a landscape more diverse than simple migration models would predict. The Sumerians of the historical period, from 3500 BC onward, when written records begin, were therefore the inheritors of this mixed ancestry. Their genetic makeup reflected multiple source populations, multiple waves of migration and admixture accumulated over thousands of years, but something distinguished them from their neighbours. The cuneiform tablets are insistent on this point. The Sumerians called themselves the black-headed people, a term that might refer to hair colour, but is used with such specificity and pride that it suggests ethnic identification. They distinguish themselves from the Akkadians, a Semitic-speaking people who lived to their north, and from the various other groups, Elamites, Gutians, Hurrians, who bordered their territory. These distinctions were not merely linguistic or cultural. The texts describe physical differences, behavioural differences, and crucially, differences in bloodline and divine favour. The city-states that emerged in Sumer during the 4th millennium BC, Uruk or Lagash, Nippur Eridu, represented something unprecedented in human history. They were true cities, with populations in the tens of thousands, monumental architecture, specialised crafts, social hierarchies, and bureaucratic administration. The invention of writing itself, around 3200 BCE, emerged from the needs of this urban complexity, beginning as a counting notation and evolving rapidly into a system capable of recording any spoken utterance. Within a few centuries, the Sumerians were producing sophisticated literature, legal codes, mathematical texts, astronomical observations, medical treatises, and the mythological narratives that concern us here. This sudden florescence, this rapid development from agricultural villages to complex urban civilization, has prompted various explanatory theories. Diffusionists in the early 20th century argued that civilization itself was invented only once in Sumer and spread from there to Egypt, India, and beyond. This view has been largely abandoned. Complex societies emerged independently in multiple locations. But the question remains, why Sumer? Why this specific location, these specific people, at this specific time? Environmental factors provide part of the answer. The Tigris and Euphrates rivers created fertile floodplains ideal for agriculture, though the floods were unpredictable and required sophisticated management through irrigation systems. This need for coordinated water management may have driven social organisation and hierarchy. Trade networks extending to the Persian Gulf, to Anatolia, to the Iranian plateau, brought resources unavailable locally, timber, stone, metals, and created wealth that could support specialist classes. The flat landscape, lacking natural defensive features, encouraged the development of diplomatic and military systems for managing conflict between city-states. But environmental determinism explains only so much. Other regions had similar conditions without producing similar civilizations at similar times. Something about the Sumerians themselves, their knowledge systems, their organizational capacity, their conceptual frameworks, enabled this transformation, and their own explanation, recorded across hundreds of tablets, is consistent, they were taught. The Anunnaki, the gods who descended from heaven before the cities existed, brought knowledge of agriculture, astronomy, mathematics, metallurgy, writing, law and governance. This knowledge was transmitted to specific lineages, to royal families and priestly clans who maintained it across generations. The system of kingship itself, according to the Sumerian king list, was lowered from heaven as a complete institution, not developed gradually through trial and error. Modern scholarship tends to treat such claims as mythological origin stories, examples of how societies legitimate their institutions through divine sanction. Kings everywhere claimed divine approval. The Sumerians were simply explicit about it. But this interpretation glosses over the specificity of the Sumerian claims. They don't merely say their kings ruled with divine blessing. They provide genealogies showing descent from specific divine ancestors. They record the names of these ancestors, describe their roles, document their relationships. They treat divine bloodlines as they treated any other administrative matter, with detailed record keeping, with careful documentation, with the same bureaucratic precision they applied to grain inventories and temple offerings. The archaeological evidence of who the Sumerians were then presents a paradox. They appear in southern Mesopotamia as a culturally distinct people speaking an isolated language, yet their genetic ancestry reflects mixing between multiple populations over thousands of years. They develop suddenly into complex civilization, yet their cities show continuity of occupation extending back millennia. They claim descent from divine beings who taught them, yet the material record shows gradual accumulation of knowledge and technique, and their language, their unique linguistic inheritance, connects to nothing in the known world, as if they brought it from somewhere else, or preserved it from something older than the archaeological record can reach. To understand what Dinar reveals about these people, we need to understand what their own texts claim about their origins. Because the correspondence between genetic evidence and ancient narrative is more precise than coincidence would predict, and stranger than either mythology or science alone can explain. The tablets speak of blood and mixture. The creation of humanity appears in multiple Sumerian and Akkadian texts, each providing different details but agreeing on fundamentals. Humans were made, not born. They were created through a deliberate process, and that process involved mixing materials from two distinct sources. The texts describe this with procedural specificity, reading less like mythological poetry and more like technical documentation. The Erigeugenesis, preserved on tablet CBS 1673 in the University of Pennsylvania Museum collection, is fragmentary but revealing. Dating to the Old Babylonian period, around 1600 BC, but recording much older Sumerian traditions, it opens with a creation narrative that is now only partially legible. What survives describes the founding of the first cities, the establishment of kingship, and then, crucially, a great flood that destroys this early civilization. The text distinguishes between the world before the flood and the world after, implying different populations, different conditions, perhaps even different types of humans. The most detailed creation account comes from the Atrahasis epic, preserved on multiple tablets, including BM 78941 in the British Museum. This Akkadian text, composed around 1700 B, draws on older Sumerian sources and provides a narrative framework that explains not just how humans were created, but why. The story begins with a labour dispute among the gods. The junior deities, the Igigi, have been tasked with digging irrigation canals, maintaining the river systems, performing the hard physical labour required to make the land productive. After 40 years of this work, they revolt, burning their tools and confronting the senior gods, the Anunnaki, who have been living in comfort while the Igigi toil. The solution proposed by Enki, the god of wisdom, is to create a substitute workforce, humans. But creating beings capable of intelligent labour requires more than shaping clay. The text describes the process in detail. A god is sacrificed, specifically the leader of the Ijiji rebellion, a god named Waila, whose name means intelligence or consciousness. The text states explicitly, "Let one god be slaughtered, and let the gods be purified by immersion. With his flesh and blood, let Nintu mix clay." Nintu, also called Beletili or Mami, is the birth goddess, the divine specialist in creation and formation. She takes the clay, the indigenous material of earth, representing the physical form, and mixes it with the flesh and blood of the sacrificed god, representing intelligence, consciousness, the divine element. The text provides the actual words Nintu speaks during this process. "I have removed your heavy labour, I have imposed your toil on man. You called out for mankind, I have loosened your yoke, I have established freedom." Then the creation itself, she pinched off 14 pieces of clay, 7 she placed on the right, 7 she placed on the left. Between them, she placed the brick. The brick serves as a birth brick, used in Mesopotamian birthing practices. 7 male and 7 female humans are created in this first generation, formed in the wombs of birth goddesses, emerging through a process that mirrors natural birth, but begins with this mixing of terrestrial and divine materials. The terminology here is worth examining closely. The Akkadian word for clay is du, but the word translated as blood is dimu, which carries connotations beyond simple physical blood. It can mean blood, red colour, life force, or essence. The flesh is ru, meaning muscle, meat, the physical substance of the body. But in combination, flesh and blood functions as an idiom meaning everything that makes someone what they are, their complete substance and essence. The text is describing the incorporation of a god's complete being, not just his physical blood, but his consciousness, his intelligence, his divine nature, into the clay that forms the human body. Another creation text, Enki and Ninmah, preserved in multiple Sumerian manuscripts and catalogued in the electronic text corpus of Sumerian literature as ETCSL 1.1.2, provides even more detail about the process and its challenges. In this narrative, after the initial creation of humans, Enki and Ninmah compete to see who can create the most interesting variations. Ninmah creates humans with various disabilities, one who cannot grasp things, one who cannot hold back urine, one who has neither male nor female genitals. For each, Enki finds a suitable social role, demonstrating the adaptability of the basic human template. Then Enki creates his own variation, but he makes it while drunk on beer, and the result is so defective that even Ninmah cannot find a use for it. The text treats creation as an experimental process, subject to error, requiring skill and attention, producing variable results depending on the exact mixture and procedure. This experimental quality appears in other texts as well. The Song of the Hoe, another Sumerian composition, describes Enlil, the chief god, breaking through the crust of the earth with a hoe, and humans sprouting up like grass from the hole. But the text specifies that this happens only after the proper preparations, only after the mould is set and the brick is ready. The imagery shifts between agricultural rudiments and manufacturing rudiments as moulded products, but both emphasize process, technique, the bringing together of components to create something new. The bloodline theme becomes explicit in text dealing with kingship. The Sumerian king list, preserved most completely on the Well-Blundell Prism 444 in the Ashmolean Museum, traces the dynasties of Sumer from the beginning of kingship to the early 2nd millennium BC. But it begins with a crucial statement. When kingship was lowered from heaven, kingship was first in Eridu. The term lowered implies a deliberate transfer, a gift or bestowal, rather than a natural emergence. And the list structure emphasizes discontinuity. It divides sharply between antediluvian kings, those who ruled before the flood, and post-diluvian kings who came after. The antediluvian rulers are given impossibly long reigns 28,800 years for one king, 43,200 for another. But the list treats them as historical, providing their names, their cities, the lengths of their rules. After the flood, the list states, the flood swept over. After the flood had swept over, when kingship was lowered again from heaven, kingship was in Kish. The repetition of lowered from heaven suggests that whatever kingship was, whatever quality or authority or bloodline it represented, had to be reintroduced after the flood destroyed it. This implies population replacement, the loss of the original royal lines, and the establishment of new dynasties carrying the same divine authority but from a fresh bestowal. Royal hymns from later Sumerian kings explicitly claim descent from these divine lines. Shulgi, king of Ur around 2100 BC, describes himself as the seed planted by Enlil in the womb, indicating not metaphorical divine favour, but literal divine ancestry. He claims his mother was the goddess Ninsun, making him semi-divine by birth. Similar claims appear for other kings. Gudea of Lagash, around 2200 BC, describes receiving kingship directly from the goddess Inanna, and calls himself the one whose seed was implanted by the good seed of the Anunnaki. The language of seed and implanting carries clear genetic connotations, describing the transmission of essential qualities from parent to offspring. The sacred marriage rituals, performed annually in major Sumerian cities, enacted this bloodline connection dramatically. The king would ritually marry the goddess Inanna, or a high priestess representing her, in a ceremony that included actual sexual intercourse. The ritual texts describe this union as transferring divine power to the king, making him capable of ruling for another year, ensuring fertility for the land and prosperity for the people. But the texts also describe it as renewing the bloodline, as mixing divine and human essences, as repeating on a ritual level what the creation narratives describe as happening literally in the beginning. The courtship of Inanna and Dumuzi, an extended cycle of love poetry exchanged between the goddess and her chosen consort, includes passages where Inanna describes Dumuzi as having been made beautiful by her favour, where his lineage is traced to divine ancestors, where their union is, presented as the proper mixing of compatible bloodlines. When the king played the role of Dumuzi in the sacred marriage, he was claiming, ritually and publicly, to carry the same bloodline as the mythological shepherd king, to be suitable for union with divinity, to produce offspring who would carry both human and divine inheritance. What does it mean that these texts describe human origins through mixing, through the combination of terrestrial clay and divine blood? At face value, they're describing genetic admixture, the creation of a hybrid population carrying ancestry from two distinct source groups. The clay could represent indigenous populations, the people who already inhabited the region. The divine blood could represent incoming populations, migrants bringing new knowledge, new technologies, new genetic markers that distinguish them sufficiently that contact seemed like an encounter with beings from another realm. This interpretation treats the texts as cultural memory, as metaphorical descriptions of actual historical events, but it requires taking seriously the possibility that ancient peoples accurately recorded their origins, that oral traditions can preserve factual information across millennia, and that we should read these texts as we would read any other historical source, with critical analysis, but not with automatic dismissal because they include elements we consider mythological. The alternative mainstream interpretation treats these texts as etiological myths, stories invented to explain observations about human nature. Humans are clearly different from animals, more intelligent, capable of complex language and culture, but also different from gods, being mortal and limited. The creation narratives explain this in-between status as resulting from mixed origins, partly clay-animal, earthly, partly divine blood telegent, conscious. This reading sees the texts as philosophy or theology, not history or biology, but the precision of the descriptions argues for something beyond pure invention. Why specify the procedural details, the pinching of clay, the number of birth goddesses, the use of the brick, the mixing process itself? Why provide multiple accounts that agree on fundamentals while differing in details, as if recording the same events from different perspectives? Why connect these creation narratives to specific bloodlines, specific families, specific claims of continued genetic inheritance? The tablets speak clearly: humans are mixtures, combinations, hybrids. Some humans, particularly royal and priestly lines, carry more of the divine component. This divine element is inherited, passes through bloodlines, can be strengthened or weakened depending on marriage choices. And it originates with the Anunnaki, the gods who came before, who created humanity for specific purposes, and whose genetic legacy continues in those who rule, who maintain temples, who preserve knowledge. What does Dinar reveal about these claims? To answer that, we need to understand what modern genetic studies show about ancient Mesopotamian populations, about admixture and ancestry, and about whether the patterns visible in molecular data correspond in any way to the patterns described in clay. Modern Dinar enters ancient Mesopotamia. The extraction of genetic material from ancient remains presents technical challenges that would have seemed insurmountable just decades ago. Dinar is a fragile molecule. In living cells, elaborate repair mechanisms constantly fix damage caused by radiation, chemical exposure, and simple copying errors. But once an organism dies, these repair systems cease. The dinner begins to break down, cleaved by enzymes, by water, by oxidation, fragmenting into smaller and smaller pieces over time. In most burial environments, dinner becomes unrecoverable within a few thousand years. Heat, moisture, and microbial activity accelerate the destruction. Cold, dry conditions preserve it longer, which is why ancient Dinar studies first succeeded with frozen mammoth remains and Ice Age humans from Siberia. Mesopotamia offers nearly the worst possible conditions for Dinar preservation. The climate is hot, the soil alternates between wet and dry with seasonal flooding, and microbial activity is intense. Early attempts to extract dinner from Sumerian skeletal remains, conducted in the 1990s and early 2000s, largely failed. The samples yielded either no dinner or hopelessly contaminated sequences dominated by modern human dinner from excavators, museum curators, and laboratory personnel. The field of ancient dinner research was progressing rapidly, producing spectacular results from European Neolithic sites, from Egyptian mummies, from pre-Columbian American burials, but Mesopotamia remained frustratingly out of reach. The breakthrough came through improvements in laboratory technique and sampling strategy. Researchers realized that the densest part of skeletal remains, the petrous portion of the temporal bone, a thick pyramid of bone protecting the inner ear, preserves Dinar better than other elements. This bone is so dense that contaminating Dinar from soil and handling penetrates only the outer surface. Samples taken from the interior, after carefully removing the surface layer, yield much purer ancient Dinar. Additionally, new Dinar extraction methods using silica columns and specialized buffers could recover shorter fragments than previous techniques, and next-generation sequencing technologies could read billions of these short fragments and computationally reassemble them into usable genetic data. The first major ancient Dinar study to include Mesopotamian samples was published in Science Journal in August 2022 by Iosif Lazaridis and an international team of geneticists and archaeologists. Titled Ancient DNA from Mesopotamia, suggests distinct pre-pottery and pottery Neolithic migrations. The study presented genetic data from individuals excavated at sites in southeastern Turkey and northern Iraq, regions that formed the northern boundary of ancient Mesopotamia and the Fertile Crescent. The sites included Ain, a pre-pottery Neolithic settlement dated to 8500–5000 BCE, and several later pottery Neolithic sites spanning the period when agriculture and village life were spreading across the region. The technical process begins with a skeletal sample, typically a piece of petrous bone or a tooth root, in a laboratory with extensive contamination controls, positive air pressure, sterilization, dedicated equipment that has never processed modern dinar. Researchers drill or cut a small sample from the interior of the bone. This sample, usually less than a gram, is ground to powder and treated with chemicals that dissolve the mineral matrix of the bone, primarily calcium lead, while preserving organic molecules including DNA. The resulting solution is passed through columns containing silica to which dinar binds. After washing away contaminants, the dinar is eluted in purified water, yielding a clear liquid containing perhaps a few nanograms of genetic material, an amount barely detectable by standard methods but sufficient for modern sequencing. The dinar, extracted from ancient samples, differs dramatically from fresh dinar. Instead of long molecules containing millions of base pairs, ancient dinar exists as short fragments, typically 30–100 base pairs long, representing random pieces of the original genome. Additionally, chemical damage has altered many of the bases. Cytosine, one of the 4 dinar bases, spontaneously degrades to uracil UU, creating characteristic patterns of false mutations that can be recognized and corrected computationally. The amount of dinar recovered varies enormously between samples. Some well-preserved remains yield enough dinar for complete genome sequencing. Others provide only mitochondrial dinar, which exists in multiple copies per cell and survives beta or small fragments of nuclear dinar, sufficient only for determining sex and basic ancestry, but not detailed analysis. The Lazaridis study successfully sequenced dinar from 15 individuals from pre-pottery Neolithic Mesopotamia, an unprecedented data set for this region and time period. The genetic analysis focused on ancestry composition, determining what proportion of each individual's dinar came from different source populations. This analysis uses the fact that human genetic variation is geographically structured. Populations that have lived in the same region for many generations share distinctive patterns of genetic variation, particular combinations of common variants that serve as signatures of ancestry. By comparing an ancient individual's dinar to the dinar of modern populations and other ancient populations whose ancestry is known, researchers can estimate what percentage of that individual's ancestry derives from different source groups. The results revealed something unexpected. The pre-pottery Neolithic individuals from Mesopotamia showed ancestry from 3 distinct sources. One component, termed Anatolian farmer ancestry, matched the genetic signature of early farming populations from central and western Turkey. These Anatolian farmers were spreading westward into Europe during the same period, carrying agriculture and distinctive genetic markers that still form a substantial component of modern European dinar. A second component, termed Caucasus hunter-gatherer ancestry, matched populations from the Caucasus Mountains region between the Black Sea and Caspian Sea. These groups were primarily foragers and herders, genetically distinct from both the Anatolian farmers and from European hunter-gatherers. The third component was more elusive, described initially as Levantine-related or basal Eurasian, representing deep ancestry related to the first modern humans who migrated out of Africa into the Middle East. Crucially, the proportions of these 3 ancestry components varied between individuals and between sites. This wasn't a case of 3 populations meeting and completely mixing into genetic uniformity. Instead, the data showed ongoing admixture, with individuals carrying different amounts of each ancestry component, suggesting continuous contact, intermarriage, and genetic exchange over many generations. Some individuals were predominantly Anatolian in ancestry, others predominantly Caucasus-related, and most were mixtures showing contributions from all three sources. This genetic pattern of mixed ancestry from multiple distinct sources corresponds precisely to what the Sumerian creation texts describe: the mixing of different essences, the combination of materials from separate origins, the production of humans who carry within them the legacy of multiple progenitors, the clay of local populations, and the divine blood of incoming groups, mixing over generations, creating a population whose genetic makeup testifies to its composite origins. But the Lazaridis study covered the pre-pottery and pottery Neolithic periods, ending around 5000 BCE. The Sumerian civilization proper emerged later, during the Ubaid period, 5400–4000 a year, and the Uruk period, 4000–3100 in southern Mesopotamia. Did these later populations show the same patterns of admixture? Were the Sumerians themselves, the black-headed people, the builders of Uruk and Ur, genetically continuous with the earlier mixed populations, or did they represent a new migration, a new mixing event? Unfortunately, direct genetic data from Sumerian sites remains limited. The preservation challenges are severe in southern Iraq, and political instability has prevented the kind of systematic sampling that the northern Mesopotamian sites received. However, a more recent study published in Nature in July 2025 provides indirect but tantalizing evidence. This study sequenced the complete genome of an individual from an Old Kingdom Egyptian cemetery at Nuwayrat, dated to approximately 2800–2600 BCE. The Egyptian individual's genetic ancestry includes a substantial Mesopotamian component. Approximately 15–20% of the genome shows affinity to populations from the Tigris-Euphrates region rather than to local Northeast African populations. This indicates genetic contact between Mesopotamia and Egypt during the crucial period when both civilizations were forming. More remarkably, the Mesopotamian ancestry component in this Egyptian individual shows the same three-way mixture observed in the earlier Mesopotamian samples: Anatolian, Caucasus, and Levantine related components in proportions consistent with continued admixture. This suggests that by the early Bronze Age, when Sumerian civilization was at its height, the characteristic genetic signature of Mesopotamian populations, this threefold mixture, had become established and was identifiable even in distant populations with Mesopotamian ancestry. The genetic studies also reveal something about population movements and replacements. At several Mesopotamian sites, the researchers detected shifts in ancestry proportions over time, indicating new arrivals or changes in demographic patterns. For example, during the transition from the Neolithic to the Bronze Age, roughly 5000–3000 B, there's an increase in ancestry components related to Iranian plateau populations, suggesting migration or genetic exchange from the east. Later, during the Bronze Age proper, there's evidence of steppe-related ancestry in populations near the Black Sea and Central Asian steppes, appearing in Mesopotamian populations, though this component remains relatively minor compared to the foundational Anatolian Caucasus-Levantine mixture. These genetic shifts don't necessarily indicate invasions or wholesale population replacements. Gene flow can occur through trade contacts, marriage alliances, small-scale migrations, or the movement of specialist groups, workers, merchants, religious specialists, between regions. But they do indicate that Mesopotamian populations were not genetically static. New ancestry components arrived, mixed with existing populations, and contributed to the genetic diversity visible in ancient remains. The question becomes, how do these population movements and admixture events correspond to the narratives preserved in Sumerian texts? The Sumerian king list speaks of kingship being lowered from heaven multiple times, of dynasties beginning in different cities, of a great flood after which everything had to be re-established. Creation texts describe humans as mixtures from the beginning. Royal inscriptions claim descent from divine bloodlines that originated with the Anunnaki before the cities existed. Are these texts recording, in mythological language, the genetic mixing events that the dinner data reveals? Are the Anunnaki themselves a cultural memory of incoming populations whose genetic distinctiveness, combined with superior knowledge or technology, made them seem divine to the existing inhabitants? To explore these questions, we need to look more closely at the specific genetic markers, the Y chromosome haplogroups and mitochondrial DNA lineages that characterize ancient Mesopotamian populations and trace their origins and distributions. Haplogroups and the Sumerian signature. If the Sumerians carried a distinctive genetic heritage, as their texts claim, we should be able to identify specific genetic markers that characterize their population. In human genetics, the clearest markers of ancestry come from two peculiar parts of the genome, the Y chromosome, which passes from father to son, essentially unchanged except for rare mutations, and mitochondrial DNA, which passes from mother to all children but continues only through daughters. These inheritance patterns create lineages that can be traced back through time, with mutations serving as markers that define branching points in the family tree of humanity. Y chromosome haplogroups are classifications of male lineages based on specific mutations in the Y chromosome. Because the Y chromosome doesn't recombine the way other chromosomes do, it preserves a clear record of paternal ancestry. A mutation that occurs in one man's Y chromosome will be passed to all his sons, and to all his sons' sons, creating a lineage defined by that mutation. As more mutations accumulate over generations, the Y chromosome family tree branches into finer and finer divisions, called haplogroups and subgroups. The predominant Y chromosome haplogroups in ancient Mesopotamian populations and in modern populations from the same region are J1, J2, G, and E1b1b. Each tells part of the story of who the Sumerians were and where their ancestors came from. Haplogroup J originated in the Middle East, probably in the northern Fertile Crescent or Caucasus region, sometime around 30,000 to 25,000 years ago. It subsequently split into two main branches, J1 and J2. Haplogroup J1 is sometimes called the Semitic haplogroup because it reaches high frequencies in Arab populations and was likely carried by the ancient Semitic peoples, including Akkadians, Assyrians, and Babylonians. Its geographic distribution today shows highest frequencies in the Arabian Peninsula, with decreasing frequencies moving outward. This suggests an Arabian or southern Mesopotamian origin for J1's expansion. Archaeological and genetic evidence indicates that J1 expanded significantly during the Bronze Age, possibly carried by Semitic-speaking populations who established kingdoms across Mesopotamia and the Levant. Haplogroup J2, by contrast, shows a distribution centered on Anatolia, the Caucasus, and the northern Fertile Crescent. Its highest frequencies today appear in populations from Turkey, Armenia, Georgia, and northern Iraq. J2 is strongly associated with the Neolithic expansion of farming, appearing in early farming sites across the region and carried westward into Europe by Neolithic migrants. The presence of J2 in ancient Mesopotamian samples from the pre-Pottery Neolithic supports the genetic finding of Anatolian Caucasus ancestry in the region's founding populations. The two J haplogroups, though related, mark different populations with different histories. J1 appears more associated with southern Mesopotamia, Arabia, and Semitic-speaking peoples. J2 associates more with northern Mesopotamia, Anatolia, and the Caucasus. The Sumerian population, if we could directly sample it, would likely show both haplogroups, reflecting the mixing of northern and southern populations in the region where Sumer emerged. Haplogroup G presents a different story. This haplogroup originated in the Caucasus or northwestern Iran around 30,000 20,000 years ago and remained largely confined to that region until the Neolithic period. Its distribution expanded dramatically during the Neolithic, appearing in early farming populations across the Fertile Crescent and eventually reaching Europe. Some of the oldest European farmer remains carry haplogroup G, indicating its role in the agricultural revolution. The presence of G in Mesopotamian populations suggests Caucasus ancestry, consistent with the genetic findings of Caucasus hunter-gatherer admixture in the region. Haplogroup E1b1b has a different origin entirely. This lineage emerged in northeast Africa, likely in the region of the Horn of Africa or the Nile Valley, around 25,000 20,000 years ago. Its presence in Mesopotamian populations indicates genetic contact with Africa, either through the Levantine corridor connecting Africa and Asia, or through more direct contact via the Red Sea and Arabian Peninsula. E1b1b reaches moderate frequencies in Middle Eastern populations and was likely present in ancient Mesopotamia as a minority component, reflecting the basal Eurasian or Levantine related ancestry detected in the genome-wide studies. These haplogroups create a genetic profile of ancient Mesopotamian populations, a mixture of lineages from the Caucasus G, from Anatolia and the northern Fertile Crescent J2, from Arabia and southern Mesopotamia J1, and from Africa or the Levant EB1b. This is precisely the pattern of admixture, the mixing of genetically distinct populations, that the Sumerian creation texts describe. But there's something more intriguing in the details. Haplogroup distribution studies of modern populations show that genetic diversity in the Middle East is unusually high compared to other regions. Most human populations show the effects of bottlenecks, founder effects, and genetic drift that reduce diversity, but Middle Eastern populations preserve ancient diversity, carrying lineages and genetic variants that disappeared elsewhere. This suggests that the region served as a genetic reservoir, a place where multiple lineages persisted and mixed, rather than one lineage replacing others. The Sumerians, if their texts are to be believed, were explicit about maintaining lineages. Royal families traced their ancestry through specific lines. Priestly families held their positions hereditarily, passing ritual knowledge and temple duties from father to son across generations. The sacred marriage rituals were carefully restricted to individuals of appropriate lineage. This cultural emphasis on bloodlines and hereditary status would have genetic consequences, creating population structure where different lineages predominated in different social classes. If the Sumerian ruling classes carried specific Y chromosome haplogroups, perhaps J2 associated with their claimed divine ancestry Caucasus Anatolian origins, bringing advanced knowledge, while the general population showed more varied ancestry including J1, G, and E1b1b, this would create the genetic equivalent of the social hierarchy described in the texts. The divine bloodlines would be identifiable as specific paternal lineages, distinguishable from the general population, though still mixed with local maternal lineages through generations of intermarriage. Unfortunately, we cannot yet test this hypothesis directly because we lack Y chromosome data from securely identified Sumerian elite burials. The Royal Cemetery of Ur, excavated in the 1920s, contains burials that are certainly elite. The individuals were buried with extraordinary wealth, with retainer sacrifices, with ritual objects indicating high status. But the skeletal remains from these burials have not yet been sampled for ancient DNA, and even if they were, assigning specific haplogroups from degraded DNA is technically challenging. However, we can examine the broader pattern. Modern populations from southern Iraq, the region where Sumer flourished, show the expected haplogroup mixture J1, J2, G, E1b1b, and other minor lineages. The frequencies don't suggest a single founding population, but rather the mixing of multiple groups. This is consistent with both the genetic data from ancient Mesopotamia and with the textual claims of mixed origins. Mitochondrial DNA, which traces maternal lineages, shows similar patterns. The predominant mitochondrial haplogroups in Middle Eastern populations include H, J, K, T, and U variants, each originating in different regions and times. Haplogroup H is the most common in Europe, deriving ultimately from Near Eastern populations. Haplogroups J, K, and T all emerged in the Middle East during the late Paleolithic or early Neolithic and expanded with farming populations. Haplogroup U variants represent older lineages, including some from hunter-gatherer populations. The presence of multiple mitochondrial haplogroups in ancient Mesopotamian samples confirms mixing of maternal lineages from different source populations. What's particularly interesting is the pattern of geographic distribution. The genetic markers most strongly associated with ancient farming populations, certain J2Y chromosome subgroups, certain mitochondrial haplogroups like K and T, show decreasing frequencies as you move away from the Middle East. They're most common in the Fertile Crescent and surrounding regions, somewhat less common in Europe, rare in East Asia and Africa. This suggests that the Middle East, and specifically the Fertile Crescent including Mesopotamia, was the source region for these lineages. Populations migrating outward carried these markers with them. The Sumerian texts claim something similar, that knowledge, civilization, and the arts of culture originated in Sumer and were transmitted outward. The Sumerian king list, after listing the early dynasties, notes that the foreign countries paid tribute to Sumerian kings, suggesting Sumer as a centre of power and influence. Later Akkadian texts describe Sumerian as the language of learning, wisdom, and religious texts, even after Akkadian had replaced it as the spoken language. The genetic evidence of Middle Eastern populations as sources for agricultural and civilizational expansions would match these textual claims, if we interpret knowledge transmission as including population movements carrying genetic markers along with cultural practices. But this raises a deeper question. If the Sumerian population was simply a mixture of the same components present throughout the Fertile Crescent, what made them distinct? Why did they speak an isolated language? Why did they develop writing and cities and sophisticated mathematics, while other populations with similar genetic ancestry did not? One possibility is that we're looking at the wrong resolution. The genetic studies to date provide regional ancestry components, Anatolian, Caucasus, Levantine, but cannot yet resolve fine-scale differences that might have existed between specific populations within those regions. Perhaps the Sumerians represented a specific mixture, a particular combination of lineages in particular proportions that occurred in southern Mesopotamia and nowhere else. Or perhaps their distinctiveness was cultural and linguistic rather than genetic, carried by a specific group whose genetic markers are not yet identifiable with available methods. Another possibility is timing. The admixture events revealed by ancient dinar occurred over millennia, with different waves of ancestry arriving at different times. The Sumerians might represent the population structure that existed at a specific moment, say 4000 BC, when the particular combination of genetic ancestry and cultural developments aligned to produce urban civilization. Later populations in the same region would have different genetic profiles due to subsequent admixture events, even though they lived in the same place. A third possibility is that the genetic distinctiveness of the Sumerians, if it existed, was subtle, involving genetic variants that current studies haven't examined. Most ancient dinar research focuses on ancestry components and major haplogroups, but functional genetic variants, genes affecting cognition, metabolism, physical traits, are beginning to be studied in ancient populations. If the Sumerians carried specific variants related to, say, numerical cognition or linguistic processing, or any of dozens of traits that might contribute to cultural development, these could have made them distinctive without creating large-scale differences in overall ancestry. The Sumerian texts, after all, don't claim that their entire population was divine or unique. They claim that specific bloodlines, specific families, specific royal and priestly lines carried divine ancestry. The general population were created as workers, as the Atrahasis epic explicitly states, to serve the gods and maintain the temples and fields. If genetic distinctiveness existed, it might have been limited to elite lineages, which might show different haplogroup frequencies or different ancestry proportions than the general population. This is testable in principle. If we could obtain Y chromosome data from Sumerian royal burials and compare it to data from non-elite burials from the same period and region, we could determine whether the elite carried specific paternal lineages. Similarly, comparing ancestry proportions between elite and non-elite burials would reveal whether social class correlated with genetic ancestry. Such studies would provide direct evidence for or against the textual claims of distinct divine bloodlines in the ruling classes. Until such data becomes available, we can note the correspondence. The genetic evidence shows mixing of multiple ancestries in Mesopotamian populations, and the Sumerian texts describe mixing of materials in the creation of humanity. The genetic evidence shows distinct paternal and maternal lineages from different source regions, and the texts describe distinct origins for the divine and earthly components of human nature. The genetic evidence suggests population structure and ongoing admixture, and the texts describe careful maintenance of bloodlines and periodic renewal of divine connection through ritual and marriage. The correspondence is striking but not conclusive. It could be coincidence or projection of modern categories onto ancient narratives. But it could also be what the Sumerians themselves claimed, an accurate record of their origins, preserved in both the molecular legacy of their dinar and the written legacy of their texts. The king list and genetic discontinuity. The Sumerian king list is one of the most peculiar documents to survive from the ancient world, preserved in multiple copies spanning nearly 1,000 years, with the most complete version inscribed on the Weld Blundell prism WB 444, dating to around 1800 BC. It presents itself as a comprehensive record of kingship in Sumer from the very beginning until the time of its composition. But that beginning is extraordinary. Kings ruling for tens of thousands of years, dynasties lasting impossibly long, spans of time that dwarf the entire recorded history of civilization. The list opens with the statement, after the kingship descended from heaven, the kingship was in Eridu. It then names the first king, Alulim, and states he ruled for 28,800 years. His successor, Alauyar, ruled for 36,000 years. The list continues through 8 kings, 5 cities, and a combined total of 241,200 years of rule. Then comes a stark transition, then the flood swept over. After the flood had swept over, and the kingship had descended from heaven, the kingship was in Kish. The post-Diluvian kings have shorter, though still exaggerated, reigns. The first king of Kish ruled for 12,100 years, implausible, but within the realm of mythological longevity claims found in other ancient traditions. Subsequent kings' reigns gradually decreased toward plausible human lifespans. By the early dynastic period, around 2500 BC, the king list is recording actual historical rulers whose reigns of 20-40 years match archaeological evidence and contemporary inscriptions. This structure impossibly long antediluvian rains, followed by a flood, followed by gradually normalising post-diluvian rains, has puzzled scholars since the document was first translated. Various explanations have been proposed. Perhaps the numbers represent not years, but months, or seasons, or some other unit that would reduce them to plausible spans. Perhaps they're purely symbolic, representing the antiquity and divine authority of early kingship rather than actual chronology. Perhaps different number systems or scribal traditions created errors that compounded over generations of copying. But there's another pattern in the king list that's harder to explain away: discontinuity. The list explicitly states that kingship descended from heaven multiple times. After the flood, it descended from heaven again, implying it had been lost and had to be re-established. Later passages describe kingship passing from city to city, from Kish to Uruk, from Uruk to Ur, from Ur to Awan, and so on, as if each transition required a new establishment of legitimate rule. The list treats kingship not as an office that one dynasty could hand to another through conquest or succession, but as a quality that had to be bestowed, that belonged to specific lineages, and that could be lost if those lineages were destroyed. This becomes more intriguing when we consider what genetic discontinuity would look like in an ancient population. If a population experiences a severe bottleneck, a dramatic reduction in population size due to catastrophe, disease, or violence, the genetic diversity of the survivors is reduced. Rare lineages are lost entirely. Common lineages survive, but in different frequencies. If new populations then migrate into the region and mix with the survivors, the genetic profile of the post-bottleneck population differs measurably from the pre-bottleneck population. Do we see such discontinuities in Mesopotamian genetic data? The answer is yes, though the timing and extent are debated. The transition from the Neolithic to the Bronze Age in Mesopotamia, roughly 5000–3000 BC, shows evidence of population turnover and the arrival of new ancestry components. Some of this change is gradual, consistent with ongoing admixture and cultural exchange, but some appears more abrupt, suggesting population movements or replacements that introduced new genetic variants in relatively short time periods. One such transition occurs around 4000 BC at the boundary between the Ubaid and Uruk periods. The Ubaid period, 6500–4000, saw the establishment of villages and towns throughout Mesopotamia, with a relatively uniform material culture suggesting cultural continuity and interaction across the region. The Uruk period, 4000–100, brought rapid urbanization, monumental architecture, increasing social stratification, and the eventual development of writing. This cultural transformation could reflect indigenous development, the Ubaid population gradually intensifying social complexity, but it could also reflect the arrival of new populations, new leadership, new knowledge systems brought by people genetically distinct from the Ubaid inhabitants. The genetic data is tantalizing but incomplete. Samples from securely dated Ubaid contexts are rare, and samples from early Uruk contexts even rarer. But the samples we have suggest continuity with admixture. The core Anatolian Caucasus-Levantine ancestry components remain, but their proportions shift and new minor components appear. This is consistent with new arrivals mixing with existing populations rather than replacing them entirely. The flood narrative in the King List and other Mesopotamian texts has long been associated with historical flood events in the Tigris-Euphrates Valley. The rivers flood annually with snowmelt from the mountains, but catastrophic floods, overtopping natural levees and inundating vast areas, occur periodically. Archaeological evidence from Sumerian cities shows flood deposits, thick layers of water laid silt with no artefacts, separating earlier and later occupation levels. Leonard Woolley, excavating at Ur in the 1920s, discovered such a flood layer and initially claimed to have found evidence of the biblical flood. Later analysis showed that flood deposits at different cities dated to different times, indicating multiple local floods rather than a single universal catastrophe. But the memory of catastrophic flooding would be culturally significant. A flood severe enough to destroy cities, kill large portions of the population, and disrupt social order would create a before and after in collective memory. If such an event also caused population movements, survivors fleeing to other regions, refugees from affected areas migrating to less damaged areas, new populations moving into depopulated regions, it would create genetic discontinuity visible in ancient dinar. The Sumerian flood narratives preserve specific details suggesting they record actual events rather than pure mythology. The Eridu Genesis, the Atrahasis epic, and the flood account in Gilgamesh all describe a specific protagonist, Ziusudra, Atrahasis, Utnapishtim, who survives by building a boat on divine instruction. After the flood recedes, this survivor makes offerings to the gods and is granted immortality or special favour. His descendants, implicitly, become the post-Diluvian humanity, or at least the post-Diluvian elite. If we read this through a genetic lens, the flood narrative preserves memory of a bottleneck event. A large population is reduced to a small number of survivors. These survivors carry only a subset of the genetic diversity present in the original population. They subsequently reproduce, repopulating the region, but the genetic makeup of the new population differs from the old. Certain lineages are lost entirely, those not carried by the survivors. Other lineages, carried by survivors, become more common through founder effects. If new populations also arrive after the catastrophe, mixing with the survivors, the post-flood genetic profile becomes a new combination. Remnants of the pre-flood population plus newcomers, creating something distinct from either source. The king list's statement that kingship descended from heaven after the flood could be read as describing the arrival of new ruling lineages. The pre-flood kings and their bloodlines were lost in the catastrophe. The post-flood kings represent new dynasties, possibly of different genetic ancestry, who established authority by claiming divine mandate, the descent of kingship from heaven, to rule over the survivors and newcomers. This interpretation treats the king list as a chronological framework preserving memory of population history. The impossibly long antediluvian reigns represent deep time, the era before reliable chronology, when oral tradition preserved only names, and the sense that the ancients ruled for vast ages. The flood marks a discontinuity, a break in continuity significant enough that everything had to be re-established afterward. The post-Diluvian section records increasingly reliable history as oral tradition gave way to written records. Modern genetic data cannot yet confirm or refute this reading. We lack ancient dinar from securely dated pre-Uruk contexts and early Uruk contexts to compare directly. But the pattern of admixture and population change over millennia does show discontinuities, periods when new ancestry components appeared, when population structure changed. If these genetic discontinuities correlate with cultural transitions visible in the archaeological record and with chronological transitions recorded in texts like the King List, we have multiple independent lines of evidence pointing to the same events. There's also the question of what descent from heaven means. Taken literally, it suggests kingship, and the royal bloodlines that embodied it came from outside the existing population. Heaven in Sumerian cosmology is not merely the sky, but the realm of the gods, the source of order and authority spatially above, but also conceptually beyond the earthly realm. If kingship descended from there, it came from elsewhere, was brought by outsiders, or was bestowed on specific individuals who then became the founders of royal lineages. If we interpret this through population genetics, descent from heaven could describe the arrival of populations from other regions who established political authority over existing inhabitants. Their genetic distinctiveness, combined with superior organizational skills or knowledge or technology, gave them the capability to rule and the cultural justification to claim divine origin. Over generations, these incoming ruling elites would intermarry with local populations, creating mixed lineages that nevertheless trace their authority to the divine ancestors who arrived from heaven, which is to say, from elsewhere. This reading makes the king list not merely a chronological document, but a genetic one, recording through the succession of dynasties the genetic history of Mesopotamian populations, the original divine bloodlines, Diluvian kings from elsewhere, the catastrophic reduction, the re-establishment of divine authority through new arrivals, descent from heaven, and the subsequent mixing and evolution of populations over historical time. The correspondence between textual narrative and genetic possibility doesn't prove the interpretation correct. Ancient texts serve many purposes beyond historical record keeping. They legitimate power, explain social hierarchies, provide religious and philosophical frameworks. The Sumerian king list could be pure ideology, inventing divine origins for rulers who were in fact no different from the populations they ruled. But the specificity argues against pure invention. Why divide history at the flood? Why mark that event as the boundary requiring kingship to descend from heaven again? Why preserve the names of antediluvian rulers if they're purely mythological? Why gradually transition from impossible to plausible reign lengths rather than maintaining mythological time throughout or starting with realistic numbers? The simplest explanation is that the king list preserves, however imperfectly, memory of actual population history, ancient ruling lineages of unclear origin, catastrophic disruption, re-establishment by new groups, and increasing historical accuracy as written. Records supplemented oral tradition. And if this reading is correct, then the genetic discontinuities visible in ancient dinar correspond to events the Sumerians themselves recorded, events significant enough to mark the boundary between epochs, between the world that was and the world that came after. Sacred marriage and bloodline legitimacy. In the spring of each year, during the month the Sumerians called Nisanu, the cities of Mesopotamia performed their most important ritual. The king, dressed in ceremonial robes, entered the temple of Inanna, the goddess of fertility, love and war. There, in the sacred chamber, he met a high priestess, or in some traditions the high priestess representing the goddess herself. What followed was not merely symbolic. The texts are explicit. The king and the priestess engaged in ritual sexual intercourse, a sacred marriage that reenacted the ancient union between Inanna and her consort Dumuzi, the shepherd king who became a god. The ritual was called the hieros gamos, Greek for sacred marriage, though the Sumerians knew it by their own terms. It was fertility magic on a grand scale, the union of divine and human ensuring fertility for the land, prosperity for the city, abundant crops and herds for the coming year. But embedded in the ritual was a deeper claim, that the king, through this union, renewed his connection to divine bloodlines, that the mixing of divine and human in the sacred marriage chamber repeated on a ritual level what the creation text described as happening literally in the beginning. The textual evidence for the sacred marriage comes from multiple sources spanning nearly 2,000 years of Mesopotamian history. Hymns describe the preparations, the processions, the exchange of love poetry between the king and the goddess. Temple records note the offerings made, the participants involved, the timing according to lunar calendars and astronomical observations. Royal inscriptions mention the sacred marriage as a source of legitimacy, proof that the gods had accepted the king and granted him the right to rule for another year. One of the most detailed accounts comes from a Sumerian hymn concerning King Idin Dagan of Isin, who ruled around 1900 BC. The text, catalogued as a CSL 2.5.3.1, describes the king's ritual marriage to Inanna in vivid detail. The goddess adorns her body and makes herself beautiful. The king approaches her with lifted head. They enter the sacred bedchamber, which is described as the house of life. The text states, the king goes with lifted head to the holy loins, goes with lifted head to the loins of Inanna. Ama Umgal lies down beside her. Ama Umgal is one of the names of Dumuzi, the role the king plays in the ritual. The hymn continues with explicit sexual imagery, unusual in cuneiform literature for its directness. He puts his hand in her hand, he puts his hand to her heart. Sweet is the sleep in the house of life, pleasant is the sleep in the house of the queen. The king goes to his loins, the king goes to the loins of Inanna. Sweet is the sleep in the house of life, pleasant is the sleep in the house of the queen. After the union, Inanna bestows blessings on the king and the city. In abundance she shall bless you. She shall protect you with a prosperous life. She shall give you a long life and everlasting breath. This isn't merely metaphorical. The ritual claims to actually transfer divine power, to actually extend the king's life, to actually ensure prosperity through the mixing of divine and human in the sexual act. Other texts make the bloodline connection even more explicit. In courtship poems between Inanna and Dumuzi, the goddess describes Dumuzi as having been chosen from the great Anunnaki, as carrying appropriate lineage, as suitable for union with divinity, precisely because his blood already contains divine elements. The marriage doesn't create divine connection from nothing, it renews and strengthens a connection that already exists through ancestry. This raises an intriguing question. Was the sacred marriage understood by its participants as purely symbolic, a ritual performance enacting mythological events? Or did they believe it accomplished something biological, something we might now describe in genetic terms, the transmission of hereditary qualities from divine to human lineages? The texts suggest the latter. Kings who performed the sacred marriage claimed its effects in their bodies, their vitality, their capability to rule. They describe themselves as having been transformed by the union, as carrying in their flesh the divine essence received from the goddess. Their children, born of queens and concubines who were themselves of appropriate lineage, inherited this quality. The royal bloodline perpetuated itself not merely through succession, but through careful breeding, through unions that maintained and concentrated the divine component. If we interpret this through modern genetics, the sacred marriage ritual could be seen as a cultural practice that maintained genetic stratification. Royal families intermarried with other royal families, or with priestly families, or with families claiming descent from particular ancestors, effectively creating a breeding population distinct from the general populace. Over generations, this would create genetic differentiation, where the elite carried different frequencies of particular genetic markers than commoners. This differentiation wouldn't necessarily be large, they're all the same species, interfertile, genetically compatible, but it could be statistically significant, detectable if we could sample DNA from elite versus non-elite burials. The emphasis on the king's loins and seed in sacred marriage texts points to paternal inheritance, to the Y chromosome lineages passed from father to son. If royal lineages maintain specific Y chromosome haplogroups through preferential marriage practices, these haplogroups would serve as genetic markers of divine descent. The sacred marriage ritual, by ensuring the king's fertility and legitimating his offspring, maintained the continuity of these Y chromosome lineages across generations. But the ritual also involved female divine figures and human priestesses, pointing to maternal inheritance to mitochondrial lineages. The high priestess who represented Inanna in the ritual was herself of special lineage, chosen from families that had provided priestesses for generations. Her mitochondrial DNA, passed to all her children, carried its own form of hereditary sacredness. The children of sacred marriages, if such unions produced offspring, which is unclear from the texts, would carry both paternal Y chromosome lineages from the king and maternal mitochondrial lineages from the priestess, combining two forms of elite genetic heritage. The ritual thus operated as a system for genetic preservation and transmission. It wasn't consciously genetic. The Sumerians had no concept of DNA or chromosomes, but they clearly understood heredity, understood that children resembled parents, that qualities passed through bloodlines, that appropriate breeding maintained desirable characteristics. The sacred marriage formalized and sacralized this understanding, making genetic continuity a religious obligation and political necessity. There's also the question of secrecy and exclusivity. The sacred marriage occurred in inner temple chambers, witnessed only by priests and select officials. The general population knew it happened, but didn't observe it directly. This exclusivity served political purposes, maintaining royal mystique, controlling access to divine power. But it could also serve genetic purposes if the ritual involved actual procreation, and if the children of such unions were raised specially, their paternity kept secret or ambiguous, their status derived from their mother's priestly lineage rather than publicly acknowledged royal fatherhood. Some scholars have argued that the sacred marriage was entirely symbolic, that the union was ritualistic rather than sexual, that the explicit language in the hymns served ceremonial purposes without describing actual acts. This interpretation treats the texts as religious poetry rather than documentary evidence. But other scholars, examining the full corpus of evidence, conclude that actual sexual intercourse was involved, performed as a ritual act with the participants understood to embody divine beings during the ceremony. If actual intercourse occurred, the question becomes, did it produce children, and if so, what happened to them? No Sumerian text explicitly identifies a child as the offspring of a sacred marriage ritual. Royal genealogies trace descent through standard dynastic succession, father to son, without mentioning ritual origins. But the absence of explicit statements doesn't mean such children didn't exist or weren't significant. In a system where bloodlines were carefully guarded and priestly lineages were hereditary, children of sacred marriages might have been integrated into priestly families, raised in temples, trained for religious roles, and understood by initiates to carry special genetic heritage even if their origins weren't publicly advertised. The broader point is that the sacred marriage ritual, like the creation narratives and the king list, presents bloodlines as central to Sumerian civilization's structure. Authority, legitimacy, and capability to perform essential roles derived from ancestry, from carrying the correct lineage, from maintaining bloodlines that trace back to divine origins. This wasn't merely ideology or mythology. It structured society, determined who could hold which positions, guided marriage alliances, and created genetic patterns that would be detectable if we could sample the ancient population with sufficient resolution. Modern Mesopotamian populations don't show obvious genetic stratification by traditional social class. There's no Y chromosome haplogroup unique to families claiming descent from ancient ruling dynasties, no mitochondrial lineage exclusive to priestly families. But we wouldn't necessarily expect such patterns to survive. Mesopotamian civilizations collapsed multiple times, conquered by Akkadians, Assyrians, Babylonians, Persians, Greeks, Arabs. Each conquest disrupted social structures, dispersed elite families, ended hereditary priesthoods. The genetic legacy of Sumerian bloodlines would have been diluted, mixed into broader populations, its distinctiveness erased by millennia of admixture. But in the 3rd millennium BC, at the height of Sumerian civilization, that genetic stratification likely existed. Royal families carrying specific Y chromosome lineages, priestly families maintaining maternal lineages through matrilineal inheritance of temple positions, both groups distinct from the general population in ancestry and genetics. The sacred marriage ritual maintained this stratification, renewed it annually, and embedded it so deeply in religious and political structures that bloodline became synonymous with legitimacy and ancestry determined destiny. What the Dina might reveal, if we could sample appropriately, is whether this cultural emphasis on bloodlines corresponded to actual genetic reality. Did Sumerian elites carry measurably different ancestry from commoners? Did they maintain specific haplogroups? Did the sacred marriage practices preserve genetic distinctiveness? These questions are answerable in principle, requiring only dinar from elite and non-elite Sumerian burials, extracted and sequenced with sufficient quality to determine haplogroups and ancestry components. The technical challenges are significant but not insurmountable. Until such data emerges, we have the texts, insistent and specific, claiming that bloodlines mattered, that divine ancestry existed in particular families, and that the mixing of divine and human continued through ritual for centuries, maintaining the genetic legacy of those who came before the cities, before the flood, before memory itself. Skeletal evidence from the royal tombs. When Leonard Woolley excavated the Royal Cemetery of Ur between 1922 and 1934, he discovered burials unlike anything previously known from ancient Mesopotamia. 16 tombs, dating to approximately 2600-2450 BC during the early dynastic III period, contained individuals buried with extraordinary wealth, gold jewellery, lapis lazuli ornaments, silver vessels, musical instruments decorated with precious materials. But most striking were the retainer burials, dozens of attendants, apparently voluntarily accompanying their rulers into death, arranged in rows, wearing their finest clothes and ornaments, some holding musical instruments, others holding weapons, all killed or drugged before the tomb was sealed. These weren't ordinary people. The richness of their grave goods, even for the attendants, indicated elite status. The individuals in the main burial chambers, the so-called kings and queens, though their actual titles are uncertain, were buried with regalia suggesting the highest political and religious authority. One, dubbed Queen Puabi, from a cylinder seal bearing her name, wore a headdress of gold leaves and flowers, lapis lazuli beads, and carnelian. Her chamber contained attendants, carts drawn by oxen with their handlers, elaborate gaming boards, and enough wealth to fund a small city-state. The question that Woolley asked, and that remains partially unanswered a century later, is who were these people? Were they rulers of Ur, buried with royal ceremony? Were they priests and priestesses, given elaborate temple burials? Were they members of specific families, specific bloodlines, whose status derived from ancestry rather than achievement? The skeletal remains themselves provide some answers. Physical anthropology, the analysis of bones to determine age, sex, health and ancestry, reveals that the individuals buried in the royal cemetery were generally healthy, well-nourished, and relatively tall for their time period. They show little evidence of heavy manual labour. Their bones lack the stress markers associated with agricultural work, brickmaking, or construction labour. They had access to quality food throughout their lives, indicated by bone density and growth patterns. Some show signs of deliberate skull modification, binding practised in infancy to elongate the skull, a practice associated with elite status in various ancient cultures. But physical anthropology has limits. Bones reveal health, diet and activities, but they don't reveal ancestry with precision. To determine whether these individuals were genetically distinct from the general Ur population requires dinar analysis, and this is where the frustration begins. The skeletal remains from the Royal Cemetery have been preserved in museums for a century, in the British Museum, the University of Pennsylvania Museum, and other collections, but they've rarely been sampled for genetic analysis, and when such sampling has been attempted, the DNA preservation has been poor. The reasons for poor preservation are multiple. First, the bones were excavated before modern archaeological methods included provisions for genetic sampling. They were cleaned, treated with preservatives, and handled extensively. This handling introduced contaminating DNA and damaged whatever ancient DNA remained. Second, the burial environment in Ur was not ideal for DNA preservation, hot climate, fluctuating moisture, microbial activity over millennia. Third, the early dynastic period dates are near the limit of ancient DNA survival in Mesopotamian contexts. DNA from colder climates or drier environments survives better and longer. Despite these challenges, recent developments in ancient DNA extraction might make analysis possible. Sampling from the petrous bone of the temporal bone, if intact specimens are available from the Royal Cemetery collections, could yield sufficient DNA for haplogroup determination and ancestry analysis. This would allow comparison between the Royal Cemetery individuals and other ancient Mesopotamian samples to determine whether the elite burials show different genetic profiles than non-elite contexts. What would we expect to find if the Sumerian claims about divine bloodlines are accurate? We'd expect the Royal Cemetery individuals to show specific Y chromosome haplogroups in male burials, possibly J2 associated with northern Caucasus ancestry rather than J1 associated with southern Arabian ancestry. Higher proportions of Caucasus-related or Anatolian-related ancestry components compared to general population samples. Evidence of close kinship between individuals in different tombs, suggesting rural burials represent an extended family or lineage rather than unrelated elite individuals. Possible distinction between kings/queens and their attendants, with the primary. Burials showing more distinctive ancestry than the retainer burials. Alternatively, if status was based on achievement, wealth, or political power rather than hereditary bloodlines, we'd expect haplogroup diversity matching the general population distribution, ancestry components matching, regional averages without elite distinctiveness, no particular kinship patterns between tombs, similar genetic profiles between primary and retainer burials, suggesting all were elite but without hereditary stratification. The available data doesn't yet allow us to distinguish between these. Possibilities for Ur specifically. But we can examine other sites where ancient DNA has been successfully extracted from Bronze Age Mesopotamian contexts. Tel Leilan in northern Syria, at the northern edge of historical Mesopotamia, has yielded skeletal remains with recoverable DNA. Analysis of these remains shows the expected admixture of Anatolian, Caucasus, and Levantine-related ancestry. But the site also shows population continuity over centuries despite political changes, suggesting that the genetic makeup of Mesopotamian populations remained relatively stable even when ruling dynasties changed. This argues against models of elite replacement and supports models of elite continuity with gradual admixture. Ain, the pre-pottery Neolithic site in southeastern Turkey, provides earlier data. The individuals buried there show significant genetic diversity, with some clustering more with Anatolian ancestry, others more with Caucasus or Levantine components. Interestingly, analysis of burial contexts suggests that individuals with different genetic ancestries were buried with similar status and treatment, implying that ancestry didn't determine status, at least in this early period before social stratification intensified. But Ain predates Sumerian civilization by thousands of years. By the early dynastic period, when complex states had emerged, when kingship was an established institution, when texts explicitly claimed hereditary authority based on bloodlines, the situation likely differed. Unfortunately, we lack comparative data from Sumerian contexts, elite versus non-elite dinar, from the same period and region, to test whether genetic stratification had emerged by that time. There are indirect approaches. Modern populations from southern Iraq carry genetic signatures that can be compared to ancient samples from elsewhere in Mesopotamia. If substantial population replacement occurred in the region since the early dynastic period, modern populations would show different genetic profiles than Bronze Age samples. If genetic continuity prevails, modern populations represent the descendants of ancient Mesopotamian populations, including both elite and non-elite lineages mixed over intervening millennia. Initial comparisons suggest continuity with admixture. Modern Iraqi populations carry the same basic ancestry components: Anatolian-related, Caucasus-related, Levantine-related, visible in ancient samples, though the proportions differ due to subsequent migrations and gene flow from surrounding regions. Haplogroup distributions in modern populations match patterns expected from ancient distributions after thousands of years of mixing. This implies that the ancient Mesopotamian population, including Sumerians, contributed genetically to modern populations, and that their genetic legacy persists. But persistence of overall ancestry doesn't address whether specific elite lineages persisted or disappeared. If Sumerian royal families carried specific Y chromosome haplogroups, and if those families were destroyed or dispersed in later conquests, those haplogroups might have decreased in frequency or disappeared from regional populations. The overall ancestry components would remain. Everyone in the region shares the same deep ancestries, but the specific paternal lineages marking elite status could be lost. This is where the textual evidence becomes crucial again. Sumerian texts record the fall of dynasties, the conquest of cities, the replacement of ruling families. The king list documents how kingship moved from city to city, dynasty to dynasty, sometimes through inheritance, but often through conquest or divine reallocation. Each such transition potentially disrupted bloodlines, ended specific lineages, removed families from power. Even if divine ancestry initially distinguished elite from commoner, the tumultuous history of Mesopotamian politics could have erased that distinction within a few centuries. Yet some lineages seem to have persisted. Priestly families maintained temple positions across political changes, suggesting that religious authority based on ancestry proved more durable than political authority. If priestly lineages preserved specific genetic markers, those markers might still be identifiable in populations claiming descent from ancient religious families. Some modern families in Iraq, particularly among communities like the Mandaeans and certain Shia clerical families, maintain strong oral traditions of ancient ancestry. Whether these traditions reflect actual genetic continuity or are mythological constructions would require dinar testing and comparison to ancient samples. The most direct answer to whether the royal cemetery individuals were genetically distinct awaits extraction of their DNA and comparison to non-elite samples from Ur. Such a study would be technically challenging, politically complex given the current situation in Iraq, and ethically sensitive given concerns about ancient dinar research and indigenous populations. But it would be definitive. If the royal cemetery burials showed distinct haplogroups or ancestry components compared to general population samples, we'd have direct evidence that elite status correlated with genetic ancestry. If they show no significant distinction, we'd have evidence that Sumerian social hierarchy was not primarily genetic, whatever the textual claims about bloodlines might suggest. Until that data emerges, we're left with suggestive correspondences, texts claiming bloodlines mattered, burial practices suggesting strong status differentiation, physical anthropology indicating elite health and treatment distinct from commoners, and genetic data from other Mesopotamian contexts showing the admixture and population structure that would be necessary for bloodline-based hierarchy to exist. The pieces fit together, but the crucial test, dinar from identified elite versus non-elite Sumerian contexts, remains to be performed. What we can say is that the possibility is real. Ancient Mesopotamian populations showed admixture from multiple sources, creating genetic diversity that could support stratification. Cultural practices emphasized hereditary authority and bloodline maintenance. The technology now exists to test whether cultural claims correspond to genetic reality. The question is no longer whether we can know, but whether we will make the effort to find out, and what it would mean for our understanding of ancient civilizations if the Sumerians were in fact accurately recording their genetic history when they inscribed their claims of divine descent in imperishable clay. The Egyptian Connection. In July 2025, the journal Nature published a study that sent ripples through the fields of Egyptology, genetics, and Near Eastern archaeology. Researchers had successfully sequenced the complete genome of an individual buried at Nuweirat, a cemetery site in Egypt's Nile Delta, dated to the Old Kingdom period around 2800-2600 BCE. This achievement alone was significant. Ancient Egyptian dinar is notoriously difficult to extract, degraded by heat and humidity, but the findings were more remarkable than the technical accomplishment. The individual's genetic ancestry included a substantial Mesopotamian component, approximately 15-20% of the genome, showing affinity to populations from the Tigris-Euphrates region rather than to local Northeast African populations. This Mesopotamian ancestry in an Old Kingdom Egyptian wasn't entirely unexpected. Archaeological evidence has long documented contact between Egypt and Mesopotamia during the pre-dynastic and early dynastic periods. Cylinder seals of Mesopotamian style appear in Egyptian contexts. Architectural elements show shared design principles. Administrative innovations, including early hieroglyphic writing, may have been influenced by Mesopotamian precedents, though the writing systems themselves developed independently. Trade routes connected the two regions via the Levantine corridor and maritime routes through the Red Sea and Persian Gulf. But genetic evidence takes the connection deeper than trade or cultural exchange. The presence of Mesopotamian ancestry in an Egyptian individual's genome indicates intermarriage, population movement, or the settlement of Mesopotamian populations in Egypt. And the timing is crucial. This individual lived during Egypt's Old Kingdom, the period when the Great Pyramids were being constructed, when pharaonic power reached its early zenith, when Egypt was establishing itself as one of the ancient world's dominant civilizations. If Mesopotamian genetic ancestry was present in Egyptian populations during this formative period, it suggests that the development of Egyptian civilization involved population contributions from the Fertile Crescent, from the region where the Sumerians had pioneered urban culture centuries earlier. The specific ancestry components in the Nuweirat genome match the Mesopotamian signature identified in other studies, a mixture of Anatolian-related, Caucasus-related, and Levantine-related ancestries. This three-way mixture is characteristic of Bronze Age Mesopotamian populations, as documented in the Lazaridis 2022 study and confirmed in subsequent analyses. The fact that this specific signature appears in Egypt suggests direct Mesopotamian contribution rather than independent local admixture producing similar patterns. What could explain Mesopotamian ancestry in Old Kingdom Egypt? Several scenarios are possible, not mutually exclusive. First, population movement from Mesopotamia to Egypt during the late 4th or early 3rd millennium BCC. This period saw political turmoil in Mesopotamia, with city-states warring, dynasties rising and falling, populations displaced by conflict. Some groups might have migrated westward through the Levant into the Nile Delta, bringing Mesopotamian genetic ancestry along with cultural knowledge and technical skills. Second, the establishment of Mesopotamian merchant or artisan colonies in Egypt. Long-distance trade networks required resident agents, specialists who could facilitate exchange, translate languages, manage logistics. If Mesopotamian traders, scribes, craftsmen or administrators settled in Egyptian cities, intermarried with local populations, their genetic contribution would appear in Egyptian burials from subsequent generations. Third, diplomatic marriages and elite alliances. As Egypt and Mesopotamian city-states developed into complex kingdoms, diplomatic relations would include marriage alliances between ruling families. A Mesopotamian princess marrying an Egyptian official, or vice versa, would introduce Mesopotamian genetic ancestry into Egyptian elite lineages. The children of such unions might become politically significant, carriers of both Egyptian and Mesopotamian bloodlines. Fourth, military conquest or recruitment. If Mesopotamian soldiers served as mercenaries in Egypt, or if Egyptian conquests included Mesopotamian territories with subsequent resettlement of prisoners or allies, genetic admixture would result. The scale required to produce the 15-20% Mesopotamian ancestry observed in the New Era individual suggests this involved more than isolated incidents, either prolonged contact over generations, or significant population movement in a shorter time frame. The Sumerian texts, interestingly, mention Egypt. They call it Magan, Meluha, or other names depending on the text and period. Trade with distant lands appears in Sumerian economic records, but the texts also occasionally mention knowledge exchange, the sending of scribes or priests to foreign lands to teach writing, mathematics, and religious practices. If such missions occurred, and if the missionaries intermarried with local elites, they would create the genetic patterns now visible in ancient DNA. There's a deeper pattern here. Multiple ancient civilizations claim founding populations with origins elsewhere, often described as civilizing heroes who brought knowledge and established order. The Egyptians had the Shemsu-Hor, the followers of Horus, who preceded the dynastic pharaohs. The Mesoamericans had Quetzalcoatl and Viracocha. The Indus Valley traditions, preserved in later Vedic texts, mention the rishis who brought sacred knowledge. These traditions are typically treated as mythology, as stories invented to legitimate institutions. But if such knowledge bearers were actual populations, migrants or traders or specialists who moved between emerging civilizations and brought technological and organizational knowledge, they would leave genetic traces corresponding to their mythological narratives. The Egyptian case is now documented genetically. An individual living in Egypt during the Old Kingdom carried Mesopotamian ancestry. This raises the question of status. Was this individual part of the elite, perhaps descended from a Mesopotamian lineage that had achieved high position in Egyptian society? Or was the Mesopotamian ancestry common enough in the Egyptian population that it appears in individuals of ordinary status? The burial context provides some clues. Nuayrat was an elite cemetery, suggesting that the sampled individual was of relatively high status. But the burial wasn't royal. This wasn't a pharaoh or immediate royal family member. The individual likely represents an official, a priest, a successful merchant, or a member of the administrative class that managed Egypt's complex bureaucracy. If this individual carried Mesopotamian ancestry, and if similar ancestry was common among Egyptian elites but rare in the general population, it would suggest that Mesopotamian migrants or their descendants concentrated in upper social strata, using their knowledge or connections to achieve high status. This mirrors the Sumerian pattern, where divine bloodlines, lineages claiming descent from the Anunnaki, were concentrated in royal and priestly families. If Mesopotamian genetic ancestry functioned similarly in Egypt, we'd expect to find it more commonly in elite burials than in common burials from the same period. Testing this hypothesis requires sampling multiple individuals from different social contexts, comparing ancestry proportions between elite and non-elite burials, and determining whether genetic ancestry correlated with social position. The implications extend beyond Egypt. If Mesopotamian populations contributed genetically to Egyptian civilization during its formative period, did similar contributions occur elsewhere? The Indus Valley civilization, contemporary with Sumer and Egypt, developed urban centres, sophisticated sanitation systems, standardized weights and measures, and an undeciphered writing system. Recent genetic studies of ancient South Asian populations have identified Western Eurasian ancestry appearing during the Bronze Age, including components related to Mesopotamian populations. Could the same pattern of population movement, knowledge transmission, and genetic admixture that connected Mesopotamia and Egypt also connect Mesopotamia and the Indus Valley? Trade routes existed. Sumerian texts mention trade with Dilmun, likely Bahrain, Magan, likely Oman, and Meluha, likely the Indus region. Archaeological evidence confirms this trade. Indus Valley beads and seals appear in Mesopotamian contexts. Mesopotamian artifacts appear in Indus sites. If trade included population movement, if merchants settled in foreign cities, if specialists travelled to provide expertise, genetic exchange would follow. The divine bloodlines that Sumerian texts describe might not be unique to Mesopotamia, but might represent a broader network of population movement across the Bronze Age world, connecting the early civilizations through both cultural and genetic exchange. This would reframe how we understand the emergence of civilization. Instead of isolated independent inventions in different regions, we'd see a connected phenomenon, populations moving along trade routes, sharing knowledge, intermarrying with local groups, creating hybrid populations that combined local and foreign ancestry. These mixed populations, carrying genetic diversity and cultural knowledge from multiple sources, would have advantages in developing complex societies. Their genetic and cultural hybridity might be the key to civilization itself, the ingredient that transforms agricultural villages into urban centres. The Sumerian texts claim exactly this, that civilization came from mixing, that humanity itself was created through the combination of divine and earthly elements, that knowledge came from the Anunnaki who brought it from elsewhere. If we read Anunnaki as a term for foreigner populations, groups who came from distant regions and seemed godlike in their knowledge and capabilities, the textual claims and the genetic evidence align. The Mesopotamian ancestry in Egypt, and potentially in other contemporary civilizations, represents the genetic signature of these knowledge bearers, these civilizing populations whose movements and admixture created the world's first complex societies. But this interpretation requires caution. Genetic ancestry doesn't determine culture. Modern genetics has firmly established that cultural practices, languages and identities are learned, not inherited through DNA. A population can adopt new cultural practices without genetic change, and genetic admixture can occur without significant cultural change. The presence of Mesopotamian ancestry in Egypt doesn't prove that Mesopotamians brought civilization to Egypt. Egyptians clearly developed their own distinctive culture, their own solutions to organisational challenges, their own artistic and architectural traditions. Yet the correlation between genetic admixture and civilizational emergence across multiple regions is striking. The Anatolian Caucasus-Levantine mixture in Mesopotamia correlates with Sumerian urbanization. The addition of Mesopotamian ancestry to Egyptian populations correlates with Old Kingdom development. The appearance of Western Eurasian ancestry in South Asia correlates with Indus Valley urbanization. These correspondences might be coincidence, or they might indicate that population mixing, the genetic and cultural exchange it represents, genuinely contributed to the emergence of social complexity. The texts from these civilizations all claim mixed origins. The Sumerians describe humanity as a mixture of clay and divine blood. The Egyptians describe the Shemsu-Hor as preceding and founding the dynasties. The Vedic texts describe the Aryans arriving and mixing with indigenous populations. Modern scholarship has often dismissed these claims as mythology, as inventions serving ideological purposes. But the genetic data suggests we should reconsider. Maybe these traditions preserve accurate memories of actual population history, of mixing events significant enough to mark the boundary between what came before and what came after, between village life and civilization. What Na reveals about Sumer's people, then, is that they were not isolated or purely indigenous. Their genetic makeup testifies to mixing, to admixture from multiple sources, to population movements and contacts that created the genetic diversity visible in ancient remains. And this same pattern appears in Egypt and potentially in other contemporary civilizations, suggesting a connected process. The genetic legacy of ancient Mesopotamia extends beyond the region, carried by populations who moved, traded, intermarried, and transferred not just genes, but knowledge, technology, and organizational systems that transformed the ancient world. The question becomes not whether such connections existed, the genetic evidence confirms they did, but what they meant. Were these movements deliberate, part of an organized expansion of knowledge and culture? Were they incidental, the natural result of trade and human mobility? Or were they something the ancients themselves described? The arrival of the Anunnaki, the descent of the gods, the coming of those whose knowledge and bloodlines transformed humanity and left a legacy detectable in both clay tablets and DNA molecules 5,000 years later. The Anunnaki described as genetic engineers. The Atrahasis epic, in its description of humanity's creation, uses terminology that is startlingly procedural. This isn't poetic imagery or vague mythological language. The text describes specific materials, specific procedures, specific agents performing specific tasks in a specific sequence. Modern readers, encountering these passages, often experience cognitive dissonance. The text reads like a technical manual, but the subject matter is supposedly mythological. What are we to make of clay mixed with blood, of birth goddesses serving as wombs, of multiple trials creating different human types? Let's examine the language closely. The Akkadian text states, Ina dilbalu ilu amli, in clay let him be alive, God and man. The word Jew appears throughout as the base material, the substrate. But this clay is repeatedly described as needing something added to it. Without the addition, it remains lifeless, inert. The addition is Dimu and Ru, from the sacrificed god Weila. The term used for mixing is Balu, which means to mix thoroughly, to blend until components are indistinguishable, the same word used for mixing beer mash or combining ingredients in cooking. The process continues, Itar ili tu mam lu ilma iten, divine spirit bound with it, man God together as one. The term Itar ili can be translated as divine spirit, but Itar more literally means essence or quintessence, the fundamental nature of something. The text is describing the essence of divinity being bound lam, to bind or attach firmly with human material so thoroughly that they become one unified entity. Then comes the crucial procedural detail. Nintu pinches off 14 pieces of clay, places 7 on the right and 7 on the left, and sets a brick between them. This brick is a birth brick. Used in Mesopotamian birthing practice, a woman in labour would squat over a brick, using it for support and to position the baby for delivery. The clay pieces are then placed in the wombs of 14 birth goddesses 7 for males, 7 for females. The text describes a period of gestation. For 10 months shall they call, then the sign of motherhood shall come. After 9 months, the Mesopotamian calendar used both 9 and 10-month counts, depending on calculation method. The first humans are born. Belet Eli opened her mouth and addressed the great gods. I have carried out perfectly the work you commanded. I have removed your hard labour. I have imposed your load on humankind. This reads like a laboratory procedure. Prepare substrate, add reagent, mix thoroughly, divide into samples, place in controlled environment, wait for specified time period, observe results. If we encountered this description in any other context, medieval alchemy, early chemistry, agricultural breeding manuals, we would recognise it as procedural documentation, instructions for reproducing an effect. The Enki and Ninmah text extends this procedural quality into experimentation and quality control. After creating the first successful humans, Enki and Ninmah engage in what the text describes as a competition, but reads more like experimental trials. Ninmah creates humans with specific defects. One cannot grasp, one cannot hold urine, one cannot see, one who has neither male nor female genitals. For each, Enki determines a social role that accommodates the defect, demonstrating the adaptability of the basic human template. Then Enki attempts his own creation, but he does so while drunk on beer, and the result is so profoundly defective that even Ninmah cannot find it suitable for any purpose. The text describes this failure. Its body lacked strength, it could not bring its arm to its mouth, its ribs were crushed, its lungs were crushed, its heart was not functional, it could not lift itself. This reads like a list of developmental abnormalities, what we'd now call a syndrome. Multiple organ systems affected by whatever went wrong in the creation process. The implication is that creating humans required precision, required correct proportions of materials, required proper procedure. Deviation produced failures. Success required expertise, knowledge of the technique, and presumably the ability to measure and mix accurately. This is craft knowledge, technical knowledge, the kind of knowledge that specialists preserve and transmit through apprenticeship. Now, let's consider what this might describe from a modern genetic perspective. If we were to describe genetic engineering to someone with no knowledge of molecular biology, using only concepts available to Bronze Age Mesopotamians, how would we do it? We might describe the genome as clay, the existing template, the base material carrying heredity. We might describe the new genetic material being introduced as essence or blood from another source, something that contains the instructions, the qualities to be transferred. We might describe the mixing process as combining these materials thoroughly so they function as one unified system. We might describe inserting this modified genome into egg cells, una of birth goontets, and allowing them to develop through normal gestation. We might describe experimental trials where the process doesn't work perfectly, producing organisms with defects. We might emphasize that the procedure requires expert knowledge, specific materials, and careful technique. This exercise isn't claiming that the Sumerians practiced genetic engineering in the modern sense, but it suggests that if a population with advanced biological knowledge were to transmit information about heredity, breeding, or even genetic manipulation to a population with limited technical vocabulary, the resulting description might look remarkably like the Atrahasis epic's creation narrative. There's another intriguing detail: the sacrificed god Weila, whose flesh and blood are mixed with clay. His name means intelligence or consciousness. The text emphasizes that his essential quality, his intelligence, is what distinguishes humans from animals. This corresponds to what geneticists would identify as the key difference between human and other primate genomes: the genes affecting brain development, cognitive capacity, language ability, If you were describing the transfer of these specific cognitive genes from one lineage to another, mixing the blood/essence of the intelligent one with clay would be a reasonable metaphorical description. The text also specifies that multiple creation events occurred. The Erudiogenesis mentions creation, but then mentions that after the flood, something had to be re-established. The King List says kingship descended from heaven, then after the flood descended again. Multiple texts mention generations of gods before the Anunnaki, different populations or groups at different times. If we're interpreting these texts as describing genetic admixture events, multiple creations would correspond to multiple waves of mixing, multiple arrivals of new populations introducing new genetic components. There's also the consistent emphasis on the purpose of creation. Humans were made to serve the gods, to perform labour, to maintain temples and fields. The Atrahasis epic is explicit. The Igigi gods were tired of working, so humans were created as a substitute labour force. This seems to conflict with modern genetic interpretations, unless we read gods as a term for the ruling class or priestly class, and humans as terms for the working population. Creating genetic or social distinctions that assign certain populations to labour and others to management would make sociological sense, however ethically problematic we find it today. Ancient societies regularly created and maintained such distinctions. Hereditary slavery existed, where the children of slaves became slaves. Caste systems divided populations into hereditary occupational categories. Aristocracies restricted intermarriage to preserve bloodlines. The Sumerian system wasn't unusual in claiming hereditary hierarchy. It was unusual in explicitly documenting the system's origins and the genetic rationale behind it. But there's a crucial question. If these texts describe actual genetic knowledge or genetic engineering, where did that knowledge come from? The Sumerians themselves attribute it to the Anunnaki, the gods who came before, who brought knowledge from elsewhere. Taking this claim seriously means proposing that a population with advanced knowledge arrived in Mesopotamia, encountered local populations, and engaged in what we'd now call genetic manipulation, or at minimum very deliberate breeding programs to create populations with desired characteristics. This moves into territory that mainstream scholarship understandably resists. It requires proposing either lost advanced civilizations predating known history, or contact with non-human intelligences, or some other explanation for how pre-urban populations could have genetic knowledge. The evidence doesn't support such claims directly, and the texts themselves can be read as mythology without requiring literal interpretation. But the correspondence between textual descriptions and genetic concepts remains striking. The emphasis on mixing materials from different sources, the procedural specificity, the experimental trials and quality control, the recognition that heredity can be manipulated through controlled breeding, the distinction between different lineages with different characteristics. All of this matches what a population with genetic knowledge would document if they wanted to record their work using available language and concepts. Perhaps the resolution is simpler. The Sumerians and their Bronze Age contemporaries understood heredity far better than we credit them with. They practiced selective breeding of plants and animals. This is undeniable from the archaeological record. They observed that children resemble parents, that certain traits run in families, that breeding choices affect offspring. They developed sophisticated knowledge of heredity through empirical observation over generations, and they described this knowledge using the language of divine intervention, not because they were ignorant or superstitious, but because that's how they conceptualized causation and agency. In this reading, the creation texts aren't describing literal genetic engineering, but are accurately describing heredity, breeding, and population admixture using mythological framing. The gods are simply ancestors, earlier populations whose hereditary contributions created the Sumerian population. The mixing is actual genetic mixing through intermarriage. The procedure is the natural process of reproduction, ritualized and sacralized because of its importance to social continuity. This interpretation preserves the accuracy of the texts as records of genetic history while avoiding claims about impossible technologies. The Sumerians accurately recorded that their population resulted from mixing multiple ancestral groups, that specific bloodlines carried specific characteristics, that heredity was important to social structure and capability. They described this in mythological terms, but the underlying information, that admixture created their population, corresponds to what genetic science now confirms. What Dina reveals, then, is that the Sumerian texts were right about the fundamental claims. Their population was mixed, origins were multiple, bloodlines did matter to social structure. Whether we interpret the creation narratives as sophisticated metaphors or as distorted memories of actual advanced knowledge is perhaps less important than recognizing that they preserve accurate information about genetic history, encoded in a form that survived 5,000 years and remains, coherent enough to test against modern science, tracing Sumerian Dinar in modern populations. If the Sumerians carried distinctive genetic signatures, specific haplogroups, particular ancestry proportions, unique combinations of genetic markers, where did those signatures go? The Sumerian civilization collapsed by the end of the 3rd millennium BC, conquered by Akkadian-speaking peoples, later by Assyrians and Babylonians, eventually absorbed into successive empires that obliterated Sumerian political independence and gradually replaced the Sumerian language with Akkadian. By 1800 BC, Sumerian survived only as a scholarly and liturgical language, like Latin in medieval Europe. The people themselves had been absorbed into the broader Mesopotamian population, but genetic lineages don't disappear when civilizations fall. Unless populations are entirely eliminated, and complete genocides are rare in history, their genetic contributions persist in descendant populations. The Dinar of ancient Sumerians continues in modern populations from Iraq and surrounding regions, mixed and diluted by millennia of subsequent admixture, but present nonetheless. We can trace these genetic legacies through two approaches: direct comparison of ancient and modern Dinar, and analysis of haplogroup distributions showing origin points and dispersal patterns. Modern populations from southern Iraq, the heartland of ancient Sumer, show Y chromosome haplogroup distributions consistent with ancient Mesopotamian ancestry. Haplogroup J1 is common, reaching frequencies around 40-50% in many Iraqi Arab populations. This haplogroup, associated with Semitic-speaking populations, probably increased in frequency after the Akkadian conquests and subsequent Arab expansions, but it was likely present in Sumerian populations as well. Haplogroup J2, associated with the Neolithic Fertile Crescent, appears at frequencies around 15-25%, representing continuity from the earliest farming populations. Haplogroup R1a, associated with later Indo-European migrations from the steppes, appears at lower frequencies, around 5-10%, representing genetic contribution from later population movements. These haplogroup distributions suggest that modern southern Iraqi populations descend from the same ancestral gene pool as ancient Sumerians, with additions from subsequent migrations. The J1 and J2 lineages particularly represent continuity with Bronze Age Mesopotamia. If we could obtain Y chromosome data from confirmed Sumerian skeletal remains and compare it to modern Iraqi populations, we'd likely see direct lineal descent, modern individuals carrying Y chromosomes identical or nearly identical to ancient Sumerian Y chromosomes, demonstrating unbroken paternal inheritance across 5,000 years. Mitochondrial DNA shows similar patterns. The dominant mitochondrial haplogroups in modern Iraqi populations, HJKTU variants, are the same haplogroups present in ancient Near Eastern populations. Haplogroup H reaches frequencies around 10–15%, representing genetic contribution from populations expanding from the Near East westward. Haplogroups J and T, originating in the Near East, appear at combined frequencies around 20–30%. These lineages connect modern populations directly to Neolithic Near Eastern ancestry, including the Sumerian period. But the genetic legacy of ancient Mesopotamia extends far beyond Iraq. The Neolithic expansion of farming from the Fertile Crescent spread Mesopotamian genetic markers across vast regions. European populations carry substantial ancestry derived from Near Eastern Neolithic farmers, including genetic components that likely originated in Mesopotamia. Approximately 40–50% of modern European ancestry comes from these Neolithic farmer populations, with the remainder from Western European hunter-gatherers and later Bronze Age steppe populations. This means that millions of modern Europeans carry genetic material that passed through ancient Mesopotamia, including potentially through Sumerian populations. Specific Y chromosome haplogroups present in Europe, certain J2 subgroups, for instance, show geographic distributions, and age estimates consistent with Bronze Age dispersal from Mesopotamia. Individuals carrying these haplogroups are, in a direct patrilineal sense, descendants of men who lived in the ancient Near East during the Bronze Age and quite possibly participated in Sumerian civilization. The geographic distribution of these lineages creates a genetic map showing dispersal from Mesopotamia. Haplogroup J2 frequencies are highest in the Fertile Crescent and decrease with distance, following both westward into Europe and eastward into Iran and Central Asia. This pattern, called an ancestry gradient, indicates the source region and direction of population movement. The fact that J2 is most common and diverse in the Mesopotamian region strongly suggests the lineage originated there or nearby and spread outward through migration. Similarly, certain mitochondrial lineages show Near Eastern origins and westward spread. Haplogroup K, for instance, originated in the Near East around 12,000–15,000 years ago and expanded into Europe with Neolithic farmers. Modern individuals carrying haplogroup K are, through direct maternal descent, connected to women who lived in the ancient Near East, potentially including Sumerian populations. Autosomal DNA, the genetic material inherited from all ancestors, not just direct paternal or maternal lines, shows similar patterns but with additional complexity. Modern Middle Eastern populations show ancestry components that genetic studies label Caucasus, Anatolian, and Levantine or similar terms. These are the same ancestry components present in ancient Mesopotamian samples, confirming genetic continuity from the Bronze Age to the present. But modern populations also show additional components reflecting subsequent admixture, Arabian ancestry from expansion out of the Arabian Peninsula, sub-Saharan African ancestry from trans-Saharan connections, European ancestry from various historical contacts, even small amounts of Central Asian ancestry from later migrations. The result is that modern populations are more genetically mixed than ancient populations, carrying ancestry from more sources, showing greater diversity. But the core Near Eastern components remain identifiable, indicating that the Bronze Age population didn't disappear but contributed genetically to all subsequent populations in the region. There's a particularly intriguing possibility regarding populations that maintain strong traditions of ancient ancestry. The marsh Arabs of southern Iraq, living in the wetlands where the Tigris and Euphrates converge, have maintained relatively isolated communities and distinct cultural practices for centuries, if not millennia. Some anthropologists have suggested they might represent greater genetic continuity with ancient Mesopotamian populations, including the Sumerians, due to their geographic isolation and cultural conservatism. Genetic studies of marsh Arab populations show haplogroup distributions similar to other Iraqi populations, but with some distinctive features, including higher frequencies of certain Y chromosome lineages and mitochondrial haplogroups that might represent preserved ancient diversity. Similarly, the Mandaean community, a religious minority in Iraq and Iran who claim ancient origins and maintain pre-Islamic religious practices with possible connections to ancient Mesopotamian traditions, might preserve genetic lineages connecting to ancient populations. The Mandaeans practice endogamy, preferentially marrying within their community, which would preserve genetic distinctiveness over time. If their tradition of ancient origins has historical basis, their genetic profiles might show closer affinity to Bronze Age Mesopotamian populations than surrounding groups who experienced more extensive admixture. Testing these possibilities requires careful genetic sampling with appropriate community consent and ethical oversight. Such studies would need to compare modern populations claiming ancient descent with ancient Dinar from confirmed Sumerian contexts, looking for specific shared haplotypes, symbinations of genetic variants inherited together that would indicate direct lineal descent. The presence of rare haplotypes shared between ancient and modern populations would provide strong evidence of genetic continuity, of specific lineages persisting across thousands of years. Beyond Iraq, we can trace potential Sumerian genetic legacy through populations that emerged from Bronze Age migrations originating in or passing through Mesopotamia. The Indo-European expansions from the steppes, which brought new languages and genetic ancestry to Europe, Iran and India, passed through or near Mesopotamia. These migrating populations would have absorbed some Mesopotamian genetic material through intermarriage and population contact. Thus, Indo-European speaking populations might carry traces of Mesopotamian ancestry acquired during these migrations, even though they're primarily descended from steppe populations. Similarly, Semitic-speaking populations expanding from the Arabian Peninsula or Levant would have mixed with Mesopotamian populations, acquiring and spreading Mesopotamian genetic markers. Modern Arabic-speaking populations throughout the Middle East and North Africa carry ancestry components traceable to the ancient Near East, including Mesopotamia. The Islamic expansions of the 7th century C and later spread these genetic components even more widely, connecting them to populations across North Africa, Spain, Central Asia, and beyond. The genetic legacy of ancient Mesopotamia, including the Sumerians, thus extends across 3 continents and contributes to the ancestry of billions of modern people. Most carry these genetic contributions in small percentages, diluted by thousands of years of mixing with other populations. But the contributions are real, detectable with modern genetic analysis, and traceable back to source populations in the ancient Near East. For individuals curious about their own potential Sumerian ancestry, consumer genetic testing provides some information, though with significant limitations. Tests from companies like 23andMe, Ancestry DNA, and similar services analyze autosomal DNA and provide ancestry composition estimates showing what percentage of an individual's genome matches reference populations from different regions. Middle Eastern or West Asian ancestry components in these reports indicate genetic connection to ancient Near Eastern populations, potentially including Mesopotamian contributions. Y chromosome and mitochondrial DNA testing, available through specialized companies like Family Tree DNA, can identify specific haplogroups. Individuals whose paternal haplogroup is J1 or J2, or whose maternal haplogroup is from the JKT or U families, carry lineages with Near Eastern origins that could include Sumerian ancestry. These haplogroups don't prove Sumerian descent. They're found in many populations from many time periods, but they demonstrate connection to the same genetic pool that contributed to ancient Mesopotamian populations. More precise determination requires comparison to ancient dinar sequences, which consumer testing companies don't currently provide. Academic studies comparing modern genomes to published ancient genomes can identify specific segments of DNA shared with ancient individuals, but this analysis requires specialized bioinformatic tools beyond what consumer services offer. As ancient DNA databases expand and analytical tools become more accessible, it may eventually be possible for individuals to determine whether they carry genetic segments specifically matching ancient Mesopotamian samples. The broader point is that genetic legacy is not the same as cultural or ethnic identity. Someone carrying Y chromosome haplogroup J2 with ultimate origins in Neolithic Mesopotamia is not Sumerian in any meaningful cultural sense. The Sumerian language, religion, social structure, and civilization are long extinct. But the genetic material, the DNA molecules, persists, copied and transmitted through countless generations, connecting modern people to ancient ancestors who built the first cities, invented writing, and recorded in cuneiform tablets the same questions about origins and ancestry that still concern us today. There's something profound in this continuity. The Sumerians themselves were deeply concerned with lineage, with bloodlines, with the transmission of essential qualities from ancestors to descendants. Their texts repeatedly emphasize genealogy, tracing kingship through specific family lines, describing divine ancestry passing through human generations. If they could know that 5,000 years later their actual genetic material persists in living populations, that their dinar continues to be copied and transmitted, they might see this as the ultimate validation of their emphasis on bloodlines and inheritance. What dinar reveals about Sumer's people, then, includes where they went. Their genetic legacy dispersed through migrations, conquests, trade, and intermarriage, spreading outward from southern Iraq to eventually contribute to populations across Europe, Asia, and North Africa. This dispersal parallels the spread of cultural innovations, writing, urban planning, mathematics, legal codes that originated in Mesopotamia and influenced subsequent civilizations. The Sumerians influenced history both genetically and culturally, both through their biological descendants and through the ideas and technologies they pioneered. The correspondence between genetic and cultural legacy raises questions about transmission mechanisms. Does genetic ancestry facilitate cultural transmission, making descendants more receptive to ancestral ideas? This seems implausible from a modern scientific perspective. Culture is learned, not inherited genetically. But historical patterns sometimes show surprising alignments. Populations carrying Neolithic Near Eastern ancestry in Europe often inhabited regions where literacy, urban culture, and technological innovation appeared earlier. This likely reflects historical and geographic factors rather than genetic ones, but the correlation exists. The Sumerians themselves might have claimed a connection. Their emphasis on divine bloodlines, carrying special capabilities, the right to rule, the ability to perform rituals, access to sacred knowledge, implicitly argues that ancestry affects capability. Modern genetics has shown that some cognitive and behavioural traits have genetic components, though these are complex, involving hundreds or thousands of genetic variants, and are heavily influenced by environment. If Sumerian ruling lineages actually did carry specific genetic variants affecting traits relevant to leadership, cognition, or social behaviour, those variants would persist in descendant populations, though in diluted and redistributed forms after millennia of mixing. Testing whether ancient elite lineages carried distinctive cognitive genetics would require identifying genetic variants associated with relevant traits in modern populations, then determining whether those variants appear at higher frequencies in ancient elite burials compared to commoner burials. This type of analysis is technically possible, but hasn't been attempted for Mesopotamian populations due to limited ancient DNA samples and ethical concerns about studying cognitive genetics in archaeological contexts. What we can say definitively is that Sumerian genetic material persists in modern populations, that this material is traceable through haplogroups and ancestry components, and that millions of living people carry direct lineal descent from individuals who participated in Sumerian civilization. Whether this genetic connection carries any functional significance beyond the purely genealogical is unknown, but the connection itself is real, documented in the dinar sequences that preserve, in molecular form, the biological legacy of humanity's first civilization. 3 interpretations of the evidence. We've examined the genetic data showing admixture in ancient Mesopotamian populations, the textual claims describing mixed origins and divine bloodlines, the archaeological evidence of complex civilization emerging in southern Iraq, and the correspondences between molecular evidence and ancient narratives. Now we must consider what this evidence means, what interpretations explain it, and what remains uncertain or unknowable. 3 broad interpretive frameworks have been proposed, each with supporting arguments and limitations. Interpretation 1, pure mythology. This view, dominant in mainstream scholarship, treats the Sumerian creation narratives, divine bloodline claims, and Anunnaki references as mythology, serving ideological functions. Kings everywhere claim divine sanction. The Sumerians simply developed particularly elaborate mythological justifications for social hierarchy and political authority. The creation texts describe mixing and divine blood not because these events literally occurred, but because this narrative explains human nature, intelligent like gods, mortal like animals, and justifies social stratification where elite bloodlines rule commoners. The genetic evidence of admixture, in this view, is coincidental. Mesopotamian populations do show mixing of multiple ancestries, but this results from the region's geographic position as a crossroads between Anatolia, the Caucasus, the Levant, and Arabia. Any population in this location would acquire mixed ancestry through routine migration and intermarriage over thousands of years. The correspondence between textual mixing narratives and genetic mixing is not evidence of historical memory, but merely reflects universal human attempts to explain diversity through origin stories. The strengths of this interpretation are its parsimony and its alignment with conventional understanding of ancient texts as primarily mythological. It requires no unusual claims about lost knowledge or advanced ancient capabilities. It treats Sumerian texts the way we treat Greek myths or Norse sagas, as culturally important literature without historical accuracy regarding supernatural events. The weaknesses are the specificity of the Sumerian claims and the precision of the correspondences. Why do creation texts describe procedural details? Why does the king list mark specific discontinuities at the flood? Why do multiple independent texts agree on fundamental claims about mixed origins? Dismissing all of this as pure invention requires explaining why the Sumerians invented these particular details rather than different ones, and why the invented details happen to match genetic evidence discovered 5,000 years later. Interpretation 2, metaphorical memory. This view treats the texts as encoding actual historical information in mythological language. The gods are human populations, the Anunnaki are earlier inhabitants or incoming migrants, and divine blood refers to genetic ancestry from these distinguished groups. The creation narratives preserve cultural memory of population admixture events, when genetically distinct groups encountered each other, intermarried, and created the mixed population that became the Sumerians. In this framework, the procedural language in creation texts describes actual breeding knowledge. Ancient peoples understood heredity through observation. They practiced selective breeding of plants and animals, recognized that children resemble parents, knew that certain traits run in families. They encoded this knowledge in mythological narratives, attributing hereditary processes to divine action because that's how they conceptualized causation. The flood narratives preserve memory of actual catastrophic events, floods, climate changes or conflicts that disrupted populations and created discontinuities visible in both archaeological and genetic records. The king list's division between antediluvian and post-diluvian periods marks a real boundary in population history, even if the specific reign lengths are mythologically exaggerated. The sacred marriage rituals enacted genetic concerns literally, maintaining royal bloodlines through controlled breeding disguised as religious ceremony. Elite families preserved specific genetic lineages through endogamy and careful marriage alliances, creating the population stratification that genetic analysis could potentially detect if suitable samples become available. The strengths of this interpretation are that it takes the text seriously as historical sources while acknowledging their mythological framing, and it explains the correspondences between textual claims and genetic evidence as resulting from accurate cultural memory. Ancient peoples accurately recorded their population history, but used available conceptual frameworks, divine action, mythological narratives to express information that we'd now describe in genetic terms. The weaknesses are the difficulty of distinguishing accurate memory from invented tradition, the problem of transmission fidelity across thousands of years of oral tradition before texts were written, and the question of how much genetic understanding we should attribute to Bronze Age populations. Did they really comprehend heredity well enough to accurately describe admixture events? Or are we projecting modern genetic concepts onto vague ancient narratives? Interpretation 3. Advanced knowledge. This view, marginal in academic scholarship but popular in alternative archaeology, takes the texts more literally. The Anunnaki were real entities, either an advanced human civilization predating known history, or non-human intelligences, or visitors from elsewhere who possessed genetic knowledge far exceeding Bronze Age capabilities. They engaged in deliberate genetic engineering, creating or modifying human populations through techniques the texts describe as mixing clay with divine blood. The procedural language in creation texts in this view is procedural because it describes actual procedures. The experiments and trials in Enki and Ninmah describe real attempts at genetic manipulation, with failures and successes recorded as they occurred. The emphasis on specific bloodlines and genealogies reflects the importance of preserving genetically modified lineages, tracking which populations carried which genetic modifications. The flood narratives preserve memory of catastrophic events, possibly global, possibly regional, that destroyed earlier advanced civilizations. The king lists in possibly long antediluvian reigns might represent different chronological systems, compressed oral traditions, or even longevity achievable through advanced knowledge now lost. The post-flood re-establishment of civilization represents survivors teaching less advanced populations, creating the rapid cultural development visible in the archaeological record. The genetic evidence of admixture, in this view, represents the mixing of advanced populations, Anunnaki, or their descendant, with indigenous populations, creating hybrid lineages that carried both ancestries. The distinctive genetics of potential elite lineages would reflect this hybridization, with royal and priestly families maintaining higher proportions of the advanced ancestry through careful breeding. The strengths of this interpretation are that it takes the texts at face value, explains the technical precision of the language, and accounts for anomalies in the archaeological record, such as the rapid emergence of complex civilization. It also explains how pre-urban populations could have genetic knowledge, if such knowledge was inherited from earlier advanced populations rather than developed independently. The weaknesses are substantial. This interpretation requires proposing entities or civilizations for which there's no direct evidence, no artifacts clearly demonstrating advanced technology, no sites showing capabilities beyond Bronze Age levels, no human remains indicating non-human biology. It conflicts with the scientific consensus on human evolution and the development of civilization. It often relies on speculative reinterpretation of ambiguous evidence and draws connections that mainstream scholarship finds unconvincing. Moreover, this interpretation risks circular reasoning. Texts are interpreted as describing advanced knowledge, then the interpretation is used as evidence that advanced knowledge existed. Without independent verification, artifacts, remains, or other evidence clearly showing capabilities beyond Bronze Age technology, the interpretation remains speculative. Evaluating the interpretations. Each framework has adherents, each can explain some evidence while struggling with other evidence, and none is definitively proven or disproven by available data. The pure mythology interpretation is safest academically, but doesn't fully account for the specificity of textual claims and genetic correspondences. The metaphorical memory interpretation is more nuanced, but requires assuming significant sophistication in how ancient peoples understood and transmitted hereditary information. The advanced knowledge interpretation takes the texts most seriously, but requires proposing entities or capabilities for which direct evidence is lacking. For most scholars, the choice between interpretations depends on broader epistemological commitments, how much credence to give ancient texts as historical sources, how to balance parsimony against explanatory power, how to handle correspondences that seem too precise to be coincidental but not, precise enough to prove causation. What's undeniable is that the evidence exists and requires explanation. Sumerian texts do claim mixed origins and divine bloodlines. Genetic data does show admixture from multiple sources in ancient Mesopotamian populations. The correspondences are real, even if their meaning is debated. And the questions the Sumerians themselves asked, who are we, where did we come from, what makes us different, remain the same questions we ask today, now with molecular tools to supplement textual analysis. Perhaps the most honest assessment is that we don't yet know which interpretation is correct, that available evidence is consistent with multiple explanations, and that definitive answers await additional data. We need more ancient dinar from Sumerian contexts, particularly from identified elite versus non-elite burials, to test whether genetic stratification existed. We need better chronological control on ancient samples to determine whether genetic discontinuities correlate with textual and archaeological transitions. We need complete genomes from multiple Sumerian individuals to search for genetic variants that might explain cognitive or cultural capabilities. Until such data emerges, the interpretive frameworks coexist, each claiming plausibility, none achieving proof. The Sumerians themselves might appreciate this ambiguity. Their literature often embraces mystery, leaving questions unanswered, acknowledging that some knowledge belongs to the gods alone. In their worldview, not everything needs explanation, not every mystery needs solving. Sometimes the question itself is the point, the wondering more valuable than the answer. What Dina reveals about Sumer's people includes this, that they were concerned with the same questions that drive modern genetics, that they recorded information we can now test with molecular tools, and that even with those tools, fundamental mysteries remain. The correspondence between ancient text and modern science is real enough to intrigue, ambiguous enough to resist simple explanation, and profound enough to suggest that however we ultimately interpret it, the Sumerians understood something important about human origins, heredity, and the deep. History encoded in both cuneiform tablets and DNA molecules. What the molecules remember. In the climate-controlled laboratory beneath the University of Pennsylvania Museum, the bone fragment from has been returned to its storage container after the DNA extraction. The genetic sequences obtained from those few milligrams of ancient bone are now digital data, strings of letters, A, C, G, T, representing the chemical bases that comprise DNA. Those sequences have been compared to thousands of other sequences from ancient and modern populations, analysed by algorithms that detect patterns invisible to human inspection, and incorporated into the growing database of human genetic diversity across time and space. The results are both illuminating and frustratingly incomplete. Yes, the individual from carried genetic ancestry from multiple sources, Anatolian, Caucasus, Levantine components, mixed in proportions characteristic of Bronze Age Mesopotamian populations. Yes, specific haplogroups can be identified, connecting this individual through direct lineal descent to populations from different regions and different times. Yes, the genetic signature matches what the Sumerian texts describe: mixing, admixture, the combination of materials from distinct origins creating something new. But the sequences don't reveal intention. They don't explain whether the admixture resulted from routine migration and intermarriage, from organised population movements, or from something more deliberate that the texts describe as divine engineering. They don't identify the individual's social status with certainty, don't confirm whether elite bloodlines carried distinctive genetics, don't answer whether claims of divine descent had biological basis or were purely ideological. The molecules remember, but their memory is fragmentary. They preserve information about ancestries and migrations, about population structure and mixing events. But they don't preserve the context, the cultural meaning, the reasons why populations moved or mixed or maintained boundaries. For that, we need the texts, the archaeology, the historical interpretation that connects molecular data to human experience. What emerges from this investigation is a picture of ancient Mesopotamian populations as fundamentally mixed, carrying genetic contributions from multiple sources, creating through admixture the biological basis for what became Sumerian civilization. The mixing was not homogeneous. Different individuals, different families, different social classes likely carried different proportions of ancestral components. This diversity within unity, this combination of distinct lineages into a functioning population, matches what the Sumerian texts describe as the essence of humanity, clay and divine blood, earthly and celestial, mixed together to create something capable of both labour and consciousness, both service and questioning. The genetic legacy of these ancient populations persists in modern descendants, though diluted and redistributed by thousands of years of subsequent history. Someone living today in southern Iraq, or Syria, or Iran, or even in Europe or other regions reached by ancient migrations, carries within their genome fragments of DNA that passed through Sumerian populations 5,000 years ago. Those fragments are molecular fossils, survivors of countless copying events, preserved because they weren't harmful enough to be eliminated by selection or unlucky enough to be lost through genetic drift. These molecular fossils don't determine culture or identity. The Sumerian civilization is extinct, its language dead, its cities ruins, its religion forgotten, except as historical curiosity. But the biological continuity remains, connecting us directly to those who first asked the questions we still ask. Who are we? Where do we come from? What distinguishes us? What legacy do we carry? The Sumerians answered these questions by recording divine origins, mixed creation, bloodlines descending from the Anunnaki. Modern genetics answers them by describing haplogroups, ancestry components, admixture events and population structure. The languages differ, the methods differ, but both approaches recognise the same fundamental reality. We are not descended from single populations, but from mixing, from the combination of distinct ancestries, from admixture events that created genetic diversity and possibly contributed to the capabilities that distinguish our species. Whether this mixing was natural, inevitable, the simple result of human mobility and fertility, or whether it involved something more directed, more intentional, more aligned with what the texts describe as divine intervention, remains uncertain. The evidence allows multiple interpretations, each plausible within its own framework, none yet proven definitively correct. What we can say with confidence is that the Sumerians cared deeply about these questions, that they developed sophisticated systems for maintaining bloodlines and documenting ancestry, and that they recorded information about their origins that modern science can now examine and partially confirm. The correspondence between textual claim and genetic evidence is too substantial to dismiss as coincidence, but too ambiguous to resolve all interpretive disputes. Perhaps that ambiguity is appropriate. The Sumerians themselves often ended their texts with acknowledgments of mystery, with statements that some knowledge remains hidden, that the ways of the gods are not fully comprehensible to humans. They were comfortable with uncertainty, with questions that lack definitive answers, with mysteries that persist despite investigation. In their cuneiform tablets, they preserve their questions and their provisional answers, recording in wedge-shaped impressions on clay what they understood and what they wondered about. In their dinar, they preserved a different kind of record, a molecular documentation of ancestries and mixing events that we are only beginning to read and understand. Both records, textual and genetic, remain incomplete. Both require interpretation, careful analysis, acknowledgement of limitations. Both point toward the same fundamental story, that the people who built the first cities, invented writing, and pioneered urban civilization were themselves products of mixing, carrying within them the legacy of multiple ancestries, multiple origins, multiple source populations, whose encounter and admixture created something unprecedented in human history. If you followed this investigation through its many turns, through genetic data and cuneiform texts, through ancient burials and modern laboratories, you've seen evidence that challenges simple narratives about human origins. The Sumerians were not simply indigenous Mesopotamians, nor simply migrants from elsewhere. They were both, and neither, a mixed population carrying genetic heritage from multiple sources, creating, through that biological diversity, the foundation for cultural innovation. Whether this mixing was natural or engineered, coincidental or deliberate, routine or exceptional, we may never know with certainty. The evidence exists, preserved in molecules and texts, waiting for additional discoveries, better analytical methods, new perspectives that might finally resolve the questions. Until then, we're left with wonder, with the recognition that 5,000 years ago, humans built cities, invented writing, developed mathematics and astronomy and law, and recorded their origins in terms that modern genetics partially confirms. They claimed they were mixed, created from distinct materials, carrying bloodlines that connected them to something divine, something beyond ordinary humanity. And the molecules, analysed with the most sophisticated tools modern science can deploy, whisper that in this, as in much else, the Sumerians might have been describing something real, something we're only beginning to understand, something encoded in both clay tablets and dinar that bridges the vast gap between the ancient world and our own, between the first questions humanity asked and the questions we're still trying to answer. The bone fragment is back in storage now, its secrets partially revealed, its mysteries preserved. Somewhere in southern Iraq, beneath ruins that were already ancient when Rome was founded, other fragments wait. More bones, more tablets, more evidence of who the Sumerians were and where they came from. Each new discovery, each new dinar sequence, each new text deciphered adds pieces to the puzzle, bringing us closer to understanding but never quite achieving complete certainty. Perhaps that's fitting. The Sumerians themselves would have understood. They knew that some questions don't have simple answers, that mystery and knowledge coexist. that the search for understanding is itself meaningful even when full understanding remains elusive. Their literature is filled with acknowledgements of limits, with passages that end not with definitive answers, but with quiet reflections on what remains unknown. In their temples, priests performed rituals at dawn and dusk, marking the boundaries between darkness and light, between the known and the mysterious. These liminal moments, these thresholds between states, held special significance. We find ourselves in a similar threshold moment now, standing between what the texts claim and what the Na suggests, between ancient wisdom and modern science, between certainty and mystery. What Dinar reveals about Sumer's people is this: they were us, and we are them, connected across 5,000 years by molecules that preserve memory in 4-letter code, by questions that transcend time, and by the recognition that who we are depends on where we came from, and that where we came from is more complex, more mixed, more mysterious than we often assume. The investigation continues in laboratories and excavation sites, in museums and universities, wherever researchers work to understand human origins and ancient civilizations. Each contribution adds knowledge, refines understanding, occasionally overturns established assumptions. The story of the Sumerians, and of human origins more broadly, remains unfinished, still being written by evidence that emerges from earth and bone and clay, still being interpreted by minds trying to bridge the vast distance between the ancient world and our own. The genetic legacy of ancient Mesopotamia flows through modern populations, invisible but detectable, connecting us to those who first asked, what does it mean to be human? The Sumerians answered by recording divine origins and mixed creation. We answer by sequencing genomes and analysing ancestry. Both approaches, separated by millennia and methodology, converge on the recognition that we are products of our genetic inheritance, that ancestry shapes us in ways both obvious and subtle, and that understanding where we came from helps illuminate who we are. Perhaps the most profound revelation is not in the specific genetic markers or the particular haplogroups, but in the recognition that the questions themselves persist. 5,000 years ago, in cities of mud brick along the Euphrates, people wondered about their origins, their distinctiveness, their connection to something greater than themselves. They wondered whether they were different from those around them, whether their bloodlines carried special qualities, whether their ancestors were extraordinary. They recorded these questions and their tentative answers in the world's first writing system, preserving them in clay that survived floods and fires and the collapse of civilizations. Today, we wonder the same things. We take DNA tests to discover our ancestry, we search genealogical records to trace our family trees, we ask whether our genetic inheritance influences who we are and what we're capable of. The methods have changed, the language has evolved, but the fundamental curiosity remains constant. We are still asking who we are, where we came from, and what makes us distinctive. The Sumerians, who lived so long ago that their cities were ancient ruins when the Bible was written, understood this persistence of questions. They knew that some mysteries endure, that each generation must grapple with fundamental uncertainties, that the search for origins and meaning is part of what makes us human. They preserved their search in cuneiform tablets, and those tablets, decoded after millennia of silence, speak to our search now. If this investigation has left you with questions, with a sense of mystery rather than closure, with wonder about what remains undiscovered, that response is appropriate. The Sumerians themselves would have approved. They didn't claim to have all answers, only to have asked the important questions and recorded what they understood, what they believed, and what they wondered about. They left their records for us, trusting that future generations would continue the investigation, would bring new tools and new perspectives, would perhaps understand things they could only glimpse, We honour that trust by taking their texts seriously, by testing their claims against the best evidence available, by acknowledging correspondences when they appear, and by maintaining humility about the limits of our understanding. The molecules remember, the tablets preserve, and somewhere in the intersection of genetic data and ancient narrative lies truth about human origins that we're still learning to read. As the quiet hours deepen, as the boundary between waking and sleep becomes permeable, these questions settle into something peaceful rather than urgent. The Sumerians are gone, their cities silent, their language extinct, but their molecules persist in living populations, their questions echo in our continued curiosity, and their legacy, both genetic and cultural, shapes the world we inhabit. What Dinar reveals about Sumer's people is ultimately this, that they were real, that their concerns were genuine, that their records preserve information we can now test and partially confirm, and that the mystery of human origins, far from being solved, deepens with each new discovery. We are connected to them through direct genetic descent, through shared questions, and through the recognition that understanding ourselves requires understanding where we came from, however complex and mixed and mysterious those origins might be. The investigation will continue long after this night ends, long after these words fade into silence and sleep. Others will extract dinar from ancient bones, decipher more tablets, develop better analytical methods, and perhaps finally resolve the questions that have persisted for 5 millennia. Until then, we have the evidence, ambiguous but substantial, pointing toward answers while preserving mystery, connecting ancient claims to modern confirmations while leaving room for wonder. And perhaps that balance between knowledge and mystery, between evidence and interpretation, between what we can prove and what we can only wonder about, is exactly right. The Sumerians knew that not everything needs explanation, that some questions matter more than their answers, that the search itself has value beyond its conclusions. So we leave it here, at the threshold between knowing and wondering, with genetic data confirming ancient claims of mixing and admixture, with textual narratives describing what molecular analysis reveals, with mysteries preserved in both clay and dinar, waiting for future discoveries to illuminate them further. The bone fragment rests in storage, the tablets wait in museums, and the questions persist, as they have for 5,000 years, as they likely will for millennia to come. What Dinar reveals about Sumer's people is that they were like us, concerned with origins, curious about ancestry, aware that who they were depended on where they came from. And what we reveal about ourselves through this investigation is that we are like them, still asking, still searching, still finding meaning in the quest to understand our genetic and cultural inheritance, our connection to those who came before, and the legacy we carry forward into whatever comes. Next, the genetic legacy of ancient Mesopotamia endures, invisible in our bloodstreams, detectable in our genomes, connecting us across vast spans of time to those who built the first cities and asked the first questions. Their answers, preserved in cuneiform and encoded in dinar, remain partially readable, partially mysterious, and entirely fascinating, a testament to human curiosity, the persistence of questions across time, and the profound connection between past and present that molecules and texts together preserve.